Kanetkar sir, can you hear me?
Yeah,
Good
I
morning.
can. Good morning.
I think there are only now I can see only 25 participants. Shall we wait for some time?
Yeah, sure.
We will wait for 5 minutes and then we'll start.
Absolutely.
Uh,
Kanetkar sir, you are presenter now. You can share your PPT or screen directly from your end.
I can't hear you. I'm unable to hear you, sir.
कोण पाटील सर बोलतात का?
Hello.
हे PD पाटील झाले का जॉईन? तो कोण PD पाटील आहेत नाही?
निंबाळकर सर बोला.
हा. तुम्ही कानेटकर सरांना काय निरोप दिला होता का?
कानेटकर सरना प्रेझेंटर केले आता. ते डायरेक्टली तिथून स्क्रीन किंवा पीपीटी शेअर करू शकतात.
ओके. हा.
सर पार्टिसिपंट्स आणि तुम्हाला माझा व्हिडिओ आणि ऑडिओ दोन्ही आय एम ऑडिबल ना?
हो. येस सर. हा, यू आर ऑडिबल सर.
या.
एक मिनिट, पॉवर मॅडम.
As I already told you, we'll be starting in say 5 minutes, as Nimbakar sir has already told me to wait for a few more minutes, and then we'll start up with the presentation.
Hello, good morning everyone. So today we are starting with the first session of the second day. So I will introduce our today's guest, Dr. Sandeep Kanetkar. Dr. Kanetkar, he has a teaching experience of over 22 years. He is working as a lecturer in Civil Engineering Department in Kusrowadia Institute of Technology, Pune. He is doing consultancy in project planning of building construction projects using Microsoft Project, water supply and drainage design, floodplain mapping and dam break analysis, and environmental impact analysis of the projects. He has conducted several training workshops on project planning and monitoring for PWD irrigation and MSCB at Yashoda. Geoinformatics application in water resources at National Water Academy, Pune, and Revit building modeling. Also GIS at Kusrowadia Institute of Technology. He has done his graduation from Bharati Vidyapit College of Engineering, Pune. Then he did his post graduation from Pune University and PhD from Pune University. His areas of interest are computer aided design and drafting of civil engineering elements to provide training in softwares like MSP, Civil 3D, Revit, QGIS, ArcGIS, ERDAS, HECRAS, SSA, WaterGems, Minitab, Excel VBA, and Python programming. And he has done development and use of multimedia e-content and learning management systems. So I will welcome once again our today's distinguished guest, Mr. Dr. Kanitkar, and I will request him to start with his session. Sir, you can start now. I think.
Yeah, sure. Thank you very much, sir. Good morning, participants. I'm Sandeep Kanitkar. First of all, on the outset, let me thank Principal Dr. Bhale Rao, sir, also head of the department, and course coordinator, our Nimbalkar, sir, both of whom are my teachers. So I thank all of them for inviting me for this particular session. The session which I am going to talk about is basically stormwater design, not focusing more on design as such, but how to use the base data, that is basically RSGIS data, for designing of a storm drainage system. So that is one of the intention of this particular session. Even though I have also worked on most of the commercial projects, say more than 3 big projects related to storm network design for urban areas. So it involves a lot of, say, base data preparation. And then finally, when all such data is ready with you, uh, basically RSGIS data and other data, then you are in a position to start design of a particular drainage system, then prepare report, proposals, and whatnot. So instead of going into all the design criteria and design process, probably as the course name is itself, basically use of RSGIS in particular water sector area. So I'll be focusing more on the RSGIS part, that is preparation of database, and what kind of data that is required for such designs, and how to process such particular data. Obviously, there is a lot of data that is required at a very large scale when you are designing for urban drainage system. So automatically covering everything and stating everything in such a short session may not be possible. And to add to that, actually demonstrating online such tools can be very difficult because of say, issues of streaming, RAM, etc. So what basically I have done today is that focus is basically what kind of data that is required for storm drainage design. So it's not directly related to research because most of you, I think, are faculty members and interested in doing research. So let us say we focus here more on the basic base data preparation, what kind of data that is required, and how to amalgamate or to bring all this data together and then take it for design of such system. And based on that, you can also have different research areas into even this area of storm network design. Like say, there will be area wherein you have research opportunity in say raster data processing, wherein you either process say digital elevation model data and have some inferences based on that, or you may have a satellite imagery and based on your processing methodology you work out say land use land cover maps of a particular region and then see the impact on the flooding or say discharge from that particular catchment. On the other part, that is the vector analysis part, what basically you have is in case of storm drainage network is lot of vector data. Uh, like say you have say road network data, which is very important because your storm networks will be aligned along the roadside. Similarly, positions of manholes, the ground elevations of all those areas, and obviously there will be area where probably survey may not be done. So because generally when you have a design of a storm drainage system, it's based on survey of made up ground. So there will be some areas where probably the surveyor will not be able to have an access. So such data either you procure from digital elevation model data or you interpolate based on contour data. And there is one more option that is available, that is topo sheets. So you import data from topo sheet of such particular study area and then you process. So likewise, there are n number of data items that are required, and my basic focus will be to see how this different data can be incorporated in design. Not necessarily that all those data items will be required, but most of them are generally required for processing and designing of a storm drainage system. So that is one of the focus. What I have done over here is there are two sections which I have divided because the total duration of this presentation is say about 1.5 hours to 2 hours. So about 1 hour I have focused on a particular session, that is wherein the presentation talks about, obviously my presentation that will be talking about how the data is collected, different forms of data that can be collected together. Obviously the data items can vary with let us say resolution point of view or depending upon access which you have, whether you are using it for research purpose or for commercial purpose, and how to process that particular data and then how to design. So that 1 hour will be totally focused on how these things are done, followed by actual demonstration of a particular storm network design, a small one, in a software called as SSA, that is Storm and Sanitary Analysis Software, which is a Autodesk product. So in order to demonstrate that, because generally what I feel all the time is whenever we deliver such lectures or in workshops, I always generally have a feeling that the participant should be able to do hands-on. But now in case of such online sessions, it is quite difficult to have two-way interaction. But through such probable demonstration, you are motivated if you are not working in RSGIS or such area which I am talking about, then probably you might be motivated to work by just knowing how these things are done. And at the same time, you impart that knowledge of how these things are done to your students as well, so that those students are motivated to work on such areas and you can help them out. The best option is that you start working on your own. You know things, either you are using it for research or for training students. So that is how your hands-on skills develop on a particular tool. Your understanding of the subject or particular that particular say course also develops to a larger extent. So from that point of view, I have used a software called as Civil 3D, which probably you are using it on day-to-day basis. So it's a Autodesk software which is available for students as well as faculty on education license purpose, as you know. So that is why I'm using it. Otherwise, there are n number of other softwares which are available, say from Bentley, which can be used or demonstrated. but deliberately I have chosen a civil 3D software which is available for education, and students and you also can use it for design of any infrastructure network, whether it be a water supply network, stormwater network, or say sewer network, or say road or any other infrastructure work. So what kind of data that is processed, that will first highlight in civil 3D, followed by, after the demonstration of civil 3D, then this data will be taken to tool called as HydraFlow, which is again inbuilt tool of civil 3D. Therein the processing of this stormwater network will be done and part design will be completed. Then again you take that data to again one more built-in tool which is there in civil 3D, that is called as SSA, or it can be used independently. Previously it was called as StormCAD. So that is now part of Autodesk. So we take that model or file to SSA and process it and simulate and work out results and see how flooding or what kind of hydrologic part has an impact on hydraulics part of pipe network likewise. So all such things, including some theoretical part plus demonstration of these three tools, everything I have combined under one video, and that video will be available to you through link which I am going to share now. What you have to do is, on WhatsApp group I have already shared the instructions part. Now I will also share the link part of that video which all participants will be watching. And important thing over here is that why I'm doing it through video session is because it's very difficult for to demonstrate a particular software like say Civil 3D and its allied plugins or say tools, and process data on a particular network live, because probably 5-10 minutes may be lost even just to load Civil 3D and other plugins, few more time to even process things likewise. So that is why such video has been used apart from whatever basic presentation which both I have compiled together. So please go through that video. Important thing over here is that during video you will be asked some questions. So probably if you are watching this video at this point of time, after say 5 minutes, probably we'll switch off this chat, and then you can switch on to that link which I will be sharing now on your WhatsApp group, and you can start watching that video during in the regular intervals. After say 5-10 minutes, there will be a question popping up in the video, which you have to answer. It's not to check your understanding of the course or subject. It is just to check whether you are watching on a regular basis on that particular time frame, and if you can answer those better. And obviously I will be collecting those answers with me, whatever video which you have gone through. As the question pop up during, as you watch video, automatically the video will stop. So so if you don't answer and if you have kept your mobile in your pocket and doing some other work, just by switching on, probably it won't help. So you'll have to complete that question and then the video will proceed further. You may watch that video 1 or 2 times as well. That means you can rewind if you want to just check what is happening, or you probably have not heard it properly likewise. But you have to complete those questions and those what we call it as a benchmarks, so that the whole video will be completed within say 50 to 60 minutes. So I will share that video, and the remaining part, I have added one more. I will be sharing that link just now. I just wanted to give some instructions so that uh, probably the coordinator is not in problem. You may not require to call him as to how to proceed. That's why I'm doing that. So the link I have shared over here, there are two videos. The first video talks about design of storm network based on RSGIS. And the second one also I felt like sharing the small video of say about 20 minutes, wherein I have tried to demonstrate in QGIS how to process few plugins. So the plugins which I think I find interesting from delivering such content to students or getting some work done from students if you are interested in, because as a faculty, if you assign students this kind of simple works, maybe during second year, first year, depends, that is also possible. So those three plugins which I have shown in second video, which you can also watch after watching this big video of say about hour duration, that particular video, small video which I have created, has three plugins in QGIS, which is an open source software for GIS. And the three plugins which I have shared and shown by demonstration, the first one talks about how to do indexing and find out which topo sheets are required for a particular study area. So for example, your students are working on a particular project, study area they have selected, and they want to acquire topo sheets. So what you generally do is you tell them the procedure. So such plugin which is available in QGIS will help them to understand which scale topo sheet can be procured from Survey of India. So please go through that demonstration, because that will be not only helpful for you to find out how these things are done, but also helpful for students also to do the project. The videos which I have already shared, first video is of about 46 to 50 minutes duration, so it will take time to watch and you will have to answer a few questions in between. The second video is of shorter duration of 20 minutes, but it has three plugins. The first plugin talks about, as I said, about this particular topo sheet indexing. The second plugin in the same video talks about how to create a 3D print file, STL file as it is called, from a digital elevation model using QGIS. So for example, let us say you are teaching surveying and you have done survey and ask students to create a STL file and take it for 3D print of that contour data or the digital elevation model which you have prepared. So it can be quite interesting project for students, as also from understanding point of view how the topography is. So how to do that in QGIS, that I have shown. And the last one is slightly simpler. That is given a digital elevation model, how to work out say cross section. Because in most of the time, say in case of HECRAS or even doing analysis in Excel, you want to have cross sections along the alignment for say floodplain modeling, stormwater modeling, and whatnot. So when you want to have such cross sections, probably you may require to have such cross section from digital elevation model to how to do that. So these are three small videos incorporated in that small video part number 2. So I hope you enjoy watching these two videos. If you are not aware of using QGIS or such a civil 3D tool, so probably that will help you. Let us say, Nimbalkar sir.
Yes, sir.
I think I will switch off this now meeting, and probably again if you want I can join after say 11:15, so that if there are any questions from participants I can answer them. So
Sir, what I
probably
want, sir, Kanetkar, sir.
yes.
Hello,
I will take
Kanetkar, sir.
instruction about, yes, go ahead.
These videos, can we directly show it here on the in this presentation?
But
Is it?
that is possible, but then probably you will not be able to answer questions. That is my intention, is that you answer questions as well. I can show videos over here as well.
The part of it which is important, because they are lengthy, no?
Yeah, it will take hardly 46 minutes for first video. So if they want to watch only one video today, it's okay. The other video they can watch it later. I can share it other some other time as well.
Okay.
So they can watch this video at their own pace till 11:15. So even though it is of 46 minutes, they can pause in between, rewind if they want, and they can continue and complete that video till 11:15. They may not complete the other video if they are not interested in watching the other video. But the video is in totality, which has all the elements. The link is already shared. you directly open the link, and as per the instructions, you please go through that WhatsApp instruction. As you open the link in browser, you may be asked to join by putting in your surname as your nickname, and then if it asks, if you are using mobile, then it may ask for using app. If you don't want to use app, that is Edpuzzle app, on the top or at the bottom there are three dots, as you know. Please click on those three dots, and from that select option called as desktop site if you are watching on mobile. So do that and start watching the video. Now probably you will have to leave this video and session to watch those videos. Only then probably you will be able to complete in time. So I hope at 11:15 again we will join, and if there are any questions I can answer them. Is it okay? The link is accessible to everyone. Everyone can join. No password required. Only thing is that they have to put in their nickname. They did not install app as well. Only thing they have to share it through desktop if they are using mobile for watching presentations. They can watch on their laptop as well. So let us meet again at 11:15. निंबाळकर सर बाहेर पडू?
हा ओके ओके ओके
ओके 11:15 ला जॉईन होतो.
ओके ओके
numeric meeting password, followed by pound.
हाँ Kanetkar sir, Kanetkar sir, hello. Kanetkar sir, हेलो
हॅलो.
हाँ सर,
हा बोला सर.
हाँ निंबाळकर बोलतोय सर. हाँ
Yes.
तुम्ही आता हाँ शेवटचं यू कॅन
जर पार्टिसिपंट्स काही क्वेश्चन्स असतील तर आय वुड बी एबल टू आन्सर. इफ नॉट दे कॅन पोस्ट इट हिअर.
Okay. See, participants are requested to ask any questions or post on chat box if you have any questions. Sir, there is one question from
That is
Sandeep.
manhole. Which type of manhole is captured, circular or rectangle? In the demonstration, it's circular, but there are different options available. So I have not specified diameter. It's I think 1.2 meter diameter, but you can have an option of both. Anything else? Participants are still watching, probably. Okay, the next question is whether we have to assume the layout of pipe network for digitization. The answer is dependent upon the road layout and the topography and the characteristics of catchment area, means what kind of catchment or the terrain is. Depending upon its characteristics, whether it's a urban area, concrete surface, grassland, forest, depending upon that you select a layout so that you can drain stormwater as early as possible. So the layout will depend upon road network and the common properties that are available from where you can align the network, and add to that you can have mixed network and then decide out of number of layouts which one is the best one. So that is actually the research area wherein you have number of layouts for the same network and try to optimize based on layout as well. So that is part of, say, a concept called as graph theory. Application of 3D map. I didn't get this question. Okay, someone has told me about GIS plugin they have used, and the audio was slightly lesser. So during recording, probably the audio recorded was slightly of lower quality. I will try to improve on that. Can you be more specific on application of 3D map? In the sense, is it from the plugin which I have discussed? Okay, so the 3D map, just take an example. For an example, you just think about a watershed. From watershed management concept, you have a 3D map of a particular watershed under study, and you have provided different watershed management structures like say bund or say check dam and whatnot. So these kind of watershed management structures you have aligned or provided, and you have created a virtual model. At the same time, you have created a physical model as well. So such physical model, if it is presented to the organization or to people, because generally these are projects which are based on public participation, so they are also able to understand the topography and the concept behind watershed management. So in such areas, the 3D print of such terrain can be useful. Other, I have already told you, as a educational tool, you can use it so that even the first year, second year students who are learning surveying, they can understand the topography better by knowing contours and a 3D model, as well as the soft contour model of the particular data. So that is probably my answer to your question. I hope you understand what I'm trying to say. Okay. Any other question?
I think, sir, there are no more questions.
Okay.
So, sir, on behalf of our institute and department, and on behalf of all the participants, I'm thankful to you for sparing your time, okay, for this session on FDP, on applications of remote sensing and GIS in water resources. So thank you very much, sir.
Thank you. The videos will be available still for a few more minutes. After that, probably the link will be lost. You, you can continue with other session. Thank you very much once again, sir.
Okay. Thank you, sir. See, for the participants, next session we are going to start immediately after 15 minutes. That is at 11:45. Dr. Thakural from National Institute of Hydrology, he will be the next speaker. He will be talking on use of irrigation, use of GIS, remote sensing and GIS in irrigation water management. Okay, so you can join immediately after at 11:45.
सर इन लोगों को एक्सेस देना है बात करने का क्या ग्रुप पे, क्या बंद कर दूं?
रहने दो, ठीक है क्या, नहीं तो यहाँ पे भी वो म्यूट ही है सारे उनको। मैंने किसी को कल हाँ जी, ठकुराल सर नमस्ते।
हाँ नमस्कार सर, नमस्कार, कैसे हैं?
हाँ नमस्ते, आपको मैंने प्रेजेंटर कर दिया है अभी यहाँ पे।
ओके।
हाँ, और हाँ, I think some in 2-3 minutes, after 2-3 minutes we will start.
ओके
हाँ?
ओके ओके ओके।
हाँ, good morning, sir.
हाँ गुड मॉर्निंग, गुड
Good
मॉर्निंग,
morning.
गुड मॉर्निंग।
I welcome you, sir, here in this FDP. Okay. Now, participants, see, today we have a session on this use of remote sensing GIS in irrigation water management. And our today's speaker is Dr. L.N. Thakural. So I will introduce, sir, Dr. Thakural. He is an alumnus of Indian Institute of Technology, Roorkee. He is graduated in civil engineering from Jamia Millia Ismailia, New Delhi in 1994. He has been awarded Diploma in Geoinformatics for Environmental Assessment and Disaster Management from Indian Institute of Remote Sensing, Dehradun in 2003. He achieved MTech with specialization in water resources development from this IIT Roorkee in 2007 and awarded with PhD on stream flow modeling and climate change from IIT Roorkee. Dr. Thakural is presently working as Scientist D in National Institute of Hydrology, Roorkee, under Ministry of Jal Shakti, Government of India. He has over 24 years of professional experience in water resources management. Uh, his specialization in remote sensing and GIS application in water resources, hydrological modeling, climate change, and irrigation water management. He has published several technical research papers in national, international journal conferences and involved in many R&D consultancy projects. He is also a member of editorial board of technical journals. Dr. Thakural have guided MTech students from IIT Roorkee, DTU Delhi, BHU Banaras, MANT Bhopal, MMUT Gorakhpur, Graphic Era University Dehradun, and internship of the students. He has been coordinator for technical visits by government official students from various academic institutions and organizations. He has been on technical visit to United Kingdom and Nepal. He is recipient of Best Research Paper Award by International Society of Science and Technology ISST, Mumbai. He has organized several national and international training programs for field engineers and academic institute. He is nodal officer for Swachh Bharat Mission, Jal Shakti Abhiyan, and the state-specific action plan for water launched by Ministry of Jal Shakti, Government of India. He is being honored with the title Swachhata Hero of Roorkee for his involvement and contribution in Swachhata program led by Government of India. He is expert member for various committees related to water resources. So now I will request Dr. Thakural sir to continue with his session. Okay. Welcome, sir.
Thank you, Dr. Nimbalkar ji. First of all, I would like to thank the organizers for giving me this opportunity to interact in this wonderful FDP session. Today, we will be talking about the application of remote sensing and geographical information system in irrigation water management. Are you able to see the slide presentation? Nimbalkar
Not
ji?
yet, sir. I think now it is there.
Okay. So today the topic is remote sensing and GIS application in irrigation water management. As we know that almost in all the fields, remote sensing and GIS being applied for various objectives. So today we will see how this can be used in irrigation water management, which is important from various aspects. We know that water as a resource is very much essential for the life, whether it is biotic as well as abiotic, livelihood of the people, and balance between the ecological system. And it is also important for the economic development. And we have seen in the past the major settlements like Harappa, Mohenjo-daro, all were along the river or the water bodies because it is required in our day-to-day activities. And we know that this resource is also crucial for the food security because we know that India is an agrarian country and water is a key for food security. We know that crops and livestock, they all need water to grow. A large amount of water is being consumed for irrigation for the agriculture purposes. And in energy security, we know that along with the agriculture, energy is required for the cultivation using different energy sectors and hydropower services, turbines, and all those. So energy security is also important, and that too requires water for operational purposes. Then when we talk about the national security of this resource, it is if we know that if water stress is there or water deficit is there in a particular region, then there are likelihoods of dispute over water and leads to the conflicts to the diminishing of fresh water supply. So it is a resource which is very much important for the food production, for the ecosystem, and the security of people. We know that the major freshwater systems are the streams and rivers, dams and reservoirs. Dams are being constructed and a reservoir is being formed on the upward side, and those are used also for the multi-purpose projects, like for the irrigation, for power generation, for domestic purpose, even for the recreation purposes at some places. Then another source of fresh water are the lakes and ponds. Especially when we talk about the Himalayan areas, then the springs are also major contributor for the fresh water. Then another most important fresh water system source is the groundwater. When we do not have rainfall over the 8 months, then the groundwater withdrawal is being done to meet out the various requirements or the demands of the community. We know that water affects all aspects of life, whether it is food production, whether it is recreational purpose, sanitation. If we are not having sanitation, there are a lot of issues. A program on this has been launched by the government of India recently, Jal Jeevan Mission, in which the objective is to provide each and every house with a functional water tap. Then talking about the energy, as I already told, that for the hydropower, power generation, running of hydropower turbines, water is needed. Then for the transport also, if you see the developed country, the major source of, we can say, mode of transport is the waterways. Now in India, it is not as much as compared to the developed countries, but we are in the progression of that. Then maintaining of the ecosystem, even for the religious functions, if we see that the rivers, these are the backbones, and we have been linked to it in the ritual forms also, and for the cultural activity. So it is affecting the all aspect of our life. If we see the India population and resources, from this we can see that we have 2% of the world's land, 4% of world's freshwater resources, almost double of that. But when we talk about the population, it is 17% of the world's population and 15% of world's cattle population. So nearly it is 32% of the population which is directly dependent upon the water. When we talk about the agriculture statistics, we see that we have 47% of the cultivated area, and of that irrigated area, that is, we are having 37% of the cultivated area, and the remaining 63% of the cultivated area, it is rain-fed area. So we can see a large area is dependent upon the rain. If we see the use of water in India, we can see from here that almost 91%, a major portion, is being used or consumed by the agriculture sector for the Indian context when we talk about. And domestic, we are using 7% of water. Almost you can see that India, China and Brazil, they are consuming more water in the agriculture sector as compared to the other countries like Russia or Germany or USA. So it is very clear that most of the water is withdrawn for the agriculture purposes in India. Now, as we talk about the climate is changing. the climate is changing due to the greenhouse gases effect. The temperature is increasing, and this is leading to the more change in the climate. And because of this, that there is an intensification of hydrological cycle, and due to which the rainfall patterns are being changing. We have witnessed in the recent past few years that rainfall intensity have increased and number of rainy days have decreased. And we can see that the demand of water in various sectors over here, if we talk about the domestic use, you can see it is almost going to be double by 2050. The demand of water that is going to be 111 billion cubic meter, which is being projected in the near future. And when we talk about the irrigation, we can also see here it is also increasing. So demand of water with the growing population and under the changing scenario becomes a challenge for meeting out the demands of water in various sectors. If we see that in India, the major challenge, because we see that rainfall is a major source of fresh water, and if we see that the rainfall spatial variance is very high, we can see in one part of the country like Rajasthan, it is around 100 mm of rainfall. And if we talk about the northeast region, the maximum rainfall, or we can say the average maximum rainfall, is 11,000 mm. So we can see how much variation is there from one part of the country to another. The maximum rainfall that occurs in the Meghalaya, earlier it was Cherrapunji, now it is Maisam, a station where we get the maximum rainfall, and minimum in the western Rajasthan. So we can see that how the temporal and the spatial variation of the rainfall is a bigger challenge for the water resources. We see that the seasonal variation during the monsoon period, almost 75% of the rainfall is there, and rest 8 months we have very less rainfall. The number of days, rainy days, those are from 5 to 150. How much seasonal variation we can see, how it is changing in spatial and temporal variations. So when we talk about the drought, and sometimes we are having wet year. So nowadays we can see that one part of country is being affected by floods and one part of country is affected by the drought at the same time. So it is, we have to see how the measures can be taken to improve the water conservation practices in the region. So as per the National Water Policy 2002 and 2012, water allocation priorities were fixed. We can see here the first priority was given to the drinking water and domestic use, and the second priority was given to the irrigation, and it is being followed by the hydropower generation and other ecology sector and others. So we can see very clearly that irrigation has the highest priority after the drinking water and the domestic uses. So we see if we are having irregular or insufficient or uncertain rains, then it leads to drought and famines. So again, the areas which are having drought and famines affect the socio-economic conditions. So irrigation can help to increase the more yield from the crops than the non-irrigated areas. And even multiple cropping in a year is possible if we are having a proper irrigation system. And moreover, we can also bring more and more land under cultivation through the irrigation system. Now, as we talked about the climate change, that it is intensifying the hydrological cycle and affecting the various variables like the spatial and temporal patterns of the precipitations. As we know that some part is affected by the flood, some is affected by drought because of the higher intensity of rainfall in a shorter duration of period. Every year we see that cities like Bombay, Mumbai, Delhi, Madras, they all are affected by the rainfall. High intensity rainfall in a shorter duration of period of time. So the problems of water drainage problems are there. And we are not able to conserve that water. Then another is the change in the ET. As the temperature being supposed to increase near the equator, it is leading to the more and more losses due to evapotranspiration, the water consumed by the plants. So more water is being required by the plants. Then it is affecting the runoff, lesser runoff, because if more evaporation is there, then lesser amount of runoff is there in the watersheds. And soil moisture, it is affecting the soil moisture conditions, and so it is being influenced by the precipitation, evaporation, and the soil moisture condition. If the soil is highly saturated, then runoff will be more. But if the temperature have increased and the ET is high, then it will lead to more and more infiltration of water will be the source of and lesser surface runoff. So the variables of interest when we talk about the irrigation water management, we need some sort of database which mostly includes the land use, then the how much is the irrigated area. In land use, we are able to find how much area is under the agriculture, how much is under the forest, how much is the urban area, and how much is the barren or the water body. So this land use information is a very important for the irrigation water management or similar studies. Then important parameter which is required for a command area is the how much is the irrigated area. In how much area, what type of crop cultivation is there, and how much is under the irrigation and how much is non-irrigated area. So this information is required for the such studies. Then what type of crop is there? What is its maturity, growing stages? What type of area it is occupying? So those sort of information on the crop is required. Then about the soil moisture conditions. So soil moisture conditions are required in the fields, because if we want to give water or irrigation, we need to know what is the condition of the soil. if we see in the developed countries, now we are having the automatic systems based on the soil moisture. If the soil moisture goes down below 70% or more, then automatically the water is being supplied to the crops. But in the countries like India, mostly the water is being supplied through the flooding system, flooding technique. Now we are moving towards the drip irrigation and the sprinklers. As we talk about the efficiency and other factors important from agriculture. Then we about talk, interest is the salinity. How much, if you are having a command area in which you are having a cultivation, and how much area is affected by the salinity, what is the, so those sort of information can be, is important for making some estimations. Then what is the rainfall? Precipitation, suppose in the Himalayan areas where the snow is also a component, so it is also required. So for precipitation also, it is a important variable for such study, and snowpack, as I told, in the Himalayan areas or Himalaya. Then the directly, non-directly observations which are required for such irrigation water management are the water use, how much water is being required, is being used, that is the evapotranspiration by the plants of different species. Then what is the production and the yields? You use various modeling for computing and estimation of the yield, and what is the water stress and the need. So these are the important information or the database which are required for our such type of studies related to irrigation water management. So here comes the role of remote sensing, because we know that especially when we talk about the bigger areas or the large areas, it is not easy to obtain the information at a, you can say, very timely or very easily. In that sense, for the bigger areas or the larger areas, we require the data information from the remote sensing. So remote sensing basically provides you with the near real-time hydrological information ranging from few hours to few days. Hydrological information, as I told you, that soil moisture, then rainfall, ET, all those information we can derive from the remote sensing data. Then that information is important depending on the temporal resolution. Temporal resolution means if we are doing some study related to flood, then in that case, if we talk about a 5-day data or 10, 15 days data, that is not required, because the flood related study, the higher temperature resolution data is required, like 6 hours data or daily data. That information is required. So it is all depending on what sort of data or is required, is on the basis of the objective of your study. Like if I am going for some flood study, then higher temporal resolution is required. If I am going for some inventory, then coarser temporal resolution data is good enough for me. When we talk about the spatial information, it ranges from meter, even less than meter, to few kilometers. Like we have a Cartosat and other data, higher resolution. Then we have coarser resolution data from MODIS, NOAA. So it all again depends upon your objective. Then the synoptic coverage, how much the area it is covering. If we are going for the field study, then the our spatial temperature, spatial information should have the good spatial or higher resolution data in comparison to the snow studies or the forest studies, like that. So keeping into mind these, the remote sensing provides you a continuous data for the your study. So basically, remote sensing is defined as a science and art of acquiring information about objects from measurement made at a distance without any physical contact with the object. And this measurement in the remote sensing is done in the form of reflectance or emittance electromagnetic radiations which are coming from the sun are being recorded and being reflected and captured by the sophisticated instruments and sensors like MSS or the radars. So basically, remote sensing includes all the methods, that is acquiring the pictures in the form of electromagnetic radiations, processing and interpretation. So why remote sensing? If we see that remote sensing is time effective, cost effective and space effective. If we talk about the manual surveys, those are costlier, time consuming. If I have to find the information about how much is the snow cover area in the Himalayas, so traditional methods are a little bit difficult. But with the help of remote sensing, a continuous data set is available. Now, lot of data is available on the internet also, like MODIS data is available, Landsat some data is also available. So data is available and it is also free of cost. So you can download that data and process. So it is providing you the cost benefit very effectively. And this data, it is a continuous data and it can be integrated for resource management with the geographical information system. It is providing the spatial data. And this also helps to provide data for a longer period. Now, as we talk about the rainfall data, now the rainfall data is available in the gridded form for the Himalayan area also. And we can see about 2000 meters, there are no observatories. So it is difficult to get the information or the data in those particular areas. So now with the help of this remote sensing, we are able to have a good database which are required for various studies, whether it is irrigation water management, whether it is snow melt runoff modeling, or it is related to forest or other. So it is providing you the lot of information which can be integrated with the geographical information system. You can see, you might be familiar with this picture, that the energy in the form of electromagnetic radiations is traveling through the atmosphere and it is coming to the surface of the earth. Some of the energy in the atmosphere is being absorbed and the energy which is coming to the surface of the earth is some energy is being transmitted through the object, is being absorbed, and some is being reflected by the object into the space band. So again, it is traveling into the atmosphere and it is being captured by instrument called sensors placed on onboard satellites. So this data or the reflectance is being captured by these instruments in the form of digital numbers, and that is being processed and provided to the users in the digital area. So it is important to note that every feature on the earth has its unique reflectance. The reflectance from a concrete material, from a water body, from a vegetation or trees, it is different. So this helps to interpret the identity of the features. So this is the electromagnetic spectrum. It is we are talking about the optical remote sensing. So it is capturing the information in the visible band, blue, green, red, and this bands capture the information of the reflectance, and that is being providing you what is the feature you can identify on the basis of these sections. Now, geographical information system commonly known as GIS, helps to develop spatial database. As I told you that when you are conducting any study related to water resources, whether it is irrigation water management, whether it is your rainfall runoff modeling, whether it is your identification of potential sites for water conservation, related to the soil studies. So all requires a huge database, spatial database. That data we are getting from the remote sensing, and that remote sensing data can be integrated into the geographical information systems. So basically, GIS is helping to integrate all this data from various sources, which are from remote sensing, which can be from topography, like Survey of India topo sheets, from socio-economic data in the forms of attributes. So these all data from various sources can be integrated to one platform. Like with the help of GIS, we are able to make many thematic layers, like soil map is there, like slope map is there, like we can say this land use map is there, then different water body inventory map is there. So all these thematic layers can be prepared in the geographical information system, and which can be used for the analysis. And specifically talking about, we can develop the water resource management studies. Like we can say how much crop area is in a particular command area, what is the area of that watershed, what is that drainage network of that area. So all those information can be generated and be used for the water resource management strategy. So we can see that Earth observing systems and water resources in this slide, whether it is optical, remote sensing, microwave using the radar and other things, lidar, the hyperspectral remote sensing, number of bands are more than 100. So it is basically these bands help to discriminate. We talk about the agriculture, they are able to identify which crop is healthier, which crop is stressed, is there any disease. So it is able to discriminate among that particular feature. And these information from this remote sensing in multidimensional data can be used using the models, hydrological models, incorporating the GIS. So we can see that various data base from different satellites, like whether it is Landsat, IRS-1A, 1B, IRS-P2, IRS-1CD, panchromatic data, OCM data, MODIS data, or whether it is ResourceSat, ReSat, Cartosat, and ICROS data. Then, so these all being categorized into different resolutions. If we talk about this Landsat, and these are coarse resolution, moderate resolution IRS data, that is 23 meter resolution, it is there. Then higher resolution which data is available, 23, 30 meter, 15 meter, this data is available. Then coarser data is there, like for MODIS data, it is available also at the 1 kilometer resolution. NOAA data is available at 1 kilometer resolution. MODIS again having sensor for 250 kilometers resolution. So basically, you have to select the sensor based on the your objective. Suppose if you want to carry out a study in the Himalayan areas, so you have to go for the coarser resolution. Then you can select the MODIS. If you want to extract the information of the snow cover area, so it is, you can go for the MODIS, NOAA, like that data. Then we have very high resolution data from Saral, Mega. So these all based on the resolution, whether it is spatial resolution or the temporal resolution, and the objective. Like if I have to go for the snowmelt, as I told that snowmelt runoff glacier, then I can go for the these MODIS and other database. Then if I want to go for the command area monitoring reservoir sedimentation, they have to go to the these IRS data, moderate resolution data. So it is all depending upon the your requirement for which sector of water resources you are going for. So these are the earth observation systems available for us to extract the information as per our demand. If we talk about the water sources, then the remote sensing has been used for various applications like land use, land cover. So for the land use, land cover, we are able to identify what type of land cover is there. Whether it is a forested area, whether it is an urban area, whether it is a water surface area, it is a reservoir or a pond like that, it is a river. So all those information on land use and land cover can be extracted using the geographical information system from a remote sensing data. So there are different techniques to classify the land use and cover maps using the classification methods. Can be your supervised classification is there, then unsupervised classification technique is there. In unsupervised, basically we form the clusters, and in supervised in unsupervised, it is the computer which is doing the whole process based on its information. In supervised classification, we train the system. We give some sample training points of the features, and on the basis of that, it classifies the satellite data, and it provides you the land use and the information. These land use and land cover are simultaneously used. Basically, land use is like how much area is under cultivation. So that is, and land cover is basically it is a natural form, and how the land is being used for our requirement is the land use. So land use and land cover information can be very easily generated in the remote sensing and GIS environment. Then for estimating the surface elevation, now we are knowing that earlier for getting the topography information, terrain information, what are the heights, elevations, we normally used to do with the help of the Survey of India topo sheets. And that was again a very tedious work. And it was also that it may vary from person to person while handling the data. But now the remote sensing data is very much in use for extracting the information on the terrain. Like if I want to get the information of the what is the elevation of our command area or the watershed, then very easily we can get the information of the elevation. What is the slope? What is the aspect? What is the drainage network in that watershed? So all these are very important informations which are required for various hydrological modeling studies. So nowadays we are having this digital elevation models which are also freely available to us on the websites. The most commonly used digital elevation models are SRTM data, then we have ASTA data also, then we have ALOS pulsar data also. So these data are freely available. The digital elevation model of DEM of ASTER and SRTM are available at 30-meter resolution. SRTM is also available at 90-meter resolution. ALOS pulsar is available at 12.5 meter of resolution. So these are basically the information for the terrain analysis. Because if we suppose if I want to design a canal in a command area, then we need to know what are the elevations. So this sort of elevation can be extracted from the SRTM. Then for the snow melt runoff modeling, so remote sensing with the help of GIS is very much important for the hydrological models. So the snow cover extent, how much is the snow cover in a particular season or on the basis of daily or weekly is available through the satellite data. Like MODIS data is there. It is providing you the snow cover extent on daily basis and weekly 8-day composite basis. So this extraction of the snow cover area, especially in the Himalayan areas, because these are sources of surface runoff to the rivers in these hilly catchments. So this snow cover extraction we can get from the snow melt runoff. Then GLOF studies. Now this data, especially talking about water resources, is very much helpful for the disaster management studies. We have seen that with the help of this, we can able to carry out the glacial lake outburst floods studies in the region. We have witnessed the 2013 Kedarnath flood, which was due to a outbursting of a lake. So those information we can extract and find the potential of these glacial lakes, how vulnerable they are for a particular region. So this is this information we can extract using the remote sensing data. Then temperature lapse rate. As we go to the higher altitude, the temperature changes with some rate. It is not constant. Earlier it was that decreasing with the rate of 0.65 degrees centigrade per 100 meters. But it is not likely that. It is changing with the season as well with the altitude. So this information on daily basis we can extract from the remote sensing data, which is helpful for the carrying out the various hydrological studies. Then in irrigation water management, with the help of this remote sensing, we are able to find what is the irrigation utilization of major, medium or minor projects, what is the irrigation performance assessment and monitoring of these, and even in the irrigation water scheduling. Basically in irrigation water scheduling, with that help, we are able to conserve our water. It is not that if we are providing more water to the crop, it will yield more. It is not like that. It may die, yield may be reduced. So if we are having a proper scheduling of irrigation, that what amount of water at what interval has to be applied, that will help you to manage the water resources for that purpose. So the efficiency of channels is also improved. It is being monitored with the help of this remote sensing satellite data. Then again, for floodplain monitoring, with the help to map the regions, areas of the water of the rivers, and we are able to provide the floodplain zoning also. Like in developed countries, we have floodplain zones. In that, we are not going for some major infrastructure. So these floodplain zoning studies are also very important. So though remote sensing is providing the length of the river, its submergence during the flood, and all those information it is providing to you for the study. Then for water resource inventory, then monitoring and forecasting. How much water body are there in your area? What is their aerial strength? You can monitor, like reservoir. In the reservoir, you are able to monitor the water spread area, and all those information you are able to make using the remote sensing and GIS. So these are some of the sensors which are being widely used in the water resources. The Cartosat 1, Cartosat 2, it is for the irrigation infrastructure mapping, new irrigation projects, surface water bodies information, tanks, ICART delineations. So this is a good, you can say, sensor for the irrigation water management. These all are for the irrigation, you can see very clearly. Then resource set list 4 data is available. Crop mapping in tank irrigation commands and at village level, reservoir sedimentation studies, of new irrigation project. Performance of the irrigation projects can also be done very easily using these sensors, like cropping pattern irrigation commands. So these are higher resolution data, and they are providing good details about the these cultivated areas on the related to cropping patterns and irrigations. Then resources AWIPS data, which is high resolution data. It is providing the seasonal cropping patterns in the irrigation commands, snow cover area monitoring. If you are having your this cultivated area in the Himalayan area, so you can get all the information from these useful sensors which are available. Some like MODIS and other are free of cost available. You can download them, process them, and use for your study. Like I already told that MODIS is a good database, sensor database is available, and it is available since 2000, and it is very much in use for extracting the aerial information of the snow cover in the hilly areas and used for the snowmelt runoff study. So that you can incorporate the component of the snowmelt in the hydrological model, for which the MODIS data sensor is very useful. So now when we talk about the irrigation water management, so basically irrigation is artificial application of water to the land to increase crop yield. Artificial application, as we have seen that in India, we have monsoon only for 4 months. Rest of the 8 months, the rainfall is very less. So sustain our crops, we need water, and that water is being applied artificially to this cultivated land, usually necessary in the arid areas or during a period of inadequate rainfall. When we are, as we are seeing that the rainfall patterns are changing due to climate change, then there are the patterns are changing. High intensity rainfall, shorter duration or so more runoff is there. The soil moisture is lesser. We are able to conserve lesser water. So under these conditions, it is very much important to go for the water storages, because this drought condition arises due to the lack of soil moistures, or the different 4 types of droughts are there: hydrological, meteorological, agriculture. So the based on the amount of rainfall deviations from the average rainfall, the soil moisture condition, those are being defined. So the mainly these irrigation are achieved by laying down a network of canals. The source of water is mainly from rivers, reservoir, lakes, or the groundwaters. A dam, barrage, reservoir is constructed to store the running water of the river, and water is diverted through these canals through a headwork to the field. So it is a schematic diagram of irrigation command. This is a river which is flowing, and a dam is being constructed over here. So a reservoir has been created here, and we can see in Khadagwasla one dam is there in Pune. So that dams basically create a reservoir, and the water which is being ponded over there is being used for various purposes. And when we talk about the irrigation, the water from this storage is being diverted through the main canal to the distributaries and to the field through these canals for the irrigation. So it is important that during the non-monsoon periods or in non-rainfed areas, irrigation plays a very important role to sustain our crops and improve or increase the yield in the command areas. So for effective water management, near real-time hydrological information and the temporal information, that is seasonal variation, spatial information, that is the point or the spatial distribution ranging from a soil map to a point rainfall, can be are the important inputs for the irrigation water management. So role of remote sensing in irrigation water management is they provide spatial crop acreages, how much crop is under different type of crops. So maps can be generated, statics can be calculated, and their growth can be monitored, and the yield can be estimated using the different models. Then evapotranspiration studies can be conducted, that is the use of water by the plants. So it is helpful. Now evaporation data is also available from the MODIS also. Using the Siebel algorithm, we are able to identify the evapotranspiration also. Then with the help of this remote sensing, we can identify and map the irrigated area. Suppose the cultivated area is, as I told you, it is 37% or like that. So how much area is under irrigation or non-irrigated area? So those sort of information can be made by identifying these, and the maps can be prepared. Then estimating the crop water stress. So from the remote sensing data, indices are being generated with the help of which you are able to find out the crop water stresses, and you are able to find the how much crop is being under stress. So these sort of can be done in irrigation water management. Then monitoring of the irrigation and drainage areas and detection of saline area. How much area is under the waterlogged, how much is the drainage monitoring, and this sort of all information we can easily do in the GIS and remote sensing. Then distinguish of the land irrigated by the surface water bodies or groundwater. How much area is being irrigated by the surface water bodies, and how much area is being irrigated using the groundwater withdrawal. So this sort of information or are very much important for irrigation water management. So these easily can be done with this technology. Then water logging and salinity problems in the irrigated, this all can be identified. Then for the GIS, we are having different software, web-based, geo browser, desktop, GIS. If we see that the proprietary software means the software which are not free of cost, they are paid. They are having a good amount for based on the modules like ArcGIS basic, we say it is ranging from 5 to 6 lakhs. Then ADAS is again there. So these two, ArcGIS and ADAS, are basically very much in use at global scale for the GIS purposes. Another software which are available are like Server, NV, they are available. But these all, among these, the ArcGIS and this ADAS imaging are very much in use. ADAS is basically for the image processing, and ArcGIS is basically for the geographical information, so GIS purposes. In image processing, like suppose if you are having an imagery and some sort of error is there, like if we talk about a scene in which there is cloud cover. So with the help of this, using several filters and other, we are able to discriminate the cloud from the other feature. So with the help of this image processing, we are able to process our remote sensing data. Then nowadays, open source softwares are also available, and among this, Elvis is also available, which is being developed by ITC Netherlands. Then we are having the QGIS, Quantum GIS, which is very much in use for GIS purposes. So QGIS is now being commonly used because it is a very easy to handle software, occupies less space, and easy to work with. So we can see here ArcGIS, which is basically interfaces like ArcCatalog, ArcMap, ArcTools, and these are organized for dealing or handling and analyzing the various data from various sources. Then this is the main window of the ArcGIS, And you can see here, these are the menu bars and other table of contents, whatever the layer you are opening over here, it is shown here. Then R catalog. R catalog is there. It is just like a window explorer. You can explore the data using this R catalog. So different features. Then again, I told you about the ADAS imaging. It is used for image processing. And this is the main window icons. This is the viewer you can see here. Whatever the data you are raster or vector you are opening, it is displayed here, and these are different icon panels of the software. Then this is the QGIS software, which is very much important nowadays and very much in use due to free of cost. You can download it from the website, and it is occupying very less space, and it uses, as it is using the interfaces and plugins, add-on plugins, which can be used at different times for various purposes. Then in irrigation water management, after GIS tools, you require another crop wet software, which is there which is being developed by FAO Rome, Italy, and it is a window-based decision support system designed to help agriculture and irrigation engineers. And the key outputs are a reference evapotransport. As I told that it is an important parameter for the such studies, crop irrigation requirement, how much water is being required, what is the irrigation requirement. All those information you can model using this crop wet software. The main key input parameters for this crop wet models are climatic data. Climatic data means your temperature, maximum, minimum, your rainfall, your solar radiations, relative humidity. So all these data is being required for computing your various outputs. This is the main window of the crop wet software. You can see. So we are we have to provide these database like climate. We are providing rainfall data, then what type of crop is there, what is the soil type, cropping pattern, and it computes the crop water and does the scheduling for the area. So basically we have input data modules are 5 and calculation modules are 3. Here these are the 3 calculation modules, and these are the input data modules: climate data, rainfall data, crop data, soil data, and crop water is done. So it is all again for this climate data we use for calculation of ET, then rainfall data for effective rainfall, how much water is available to the crops, then crop data and planting data. So at what type it is being planted, what is the sowing time, and what is the ripening time. So those information is being inputted. Then what is the type of soil for irrigation, because it all depend about the type of the soil. Then the cropping patterns. So these input models are data is provided into the this software, and we are able to generate our calculations. How much crop water is requirement, because it is seen that providing excess amount of water to the crop is not useful. So for that, it is important we have to calculate how much water is required by a particular crop and what is its irrigation requirements. On that basis, we supply the water from the head source to the fields. So the crop is not provided water which is not desirable for its growth. So these are some of the windows of data sets which are being for the software. So this is the format in which you provide the data. When you click on this rainfall, you get the months over here and you provide the rainfall over here. And you can select the method of calculating the effective rainfall. It is based on a particular station. Observed rainfall is there. You provide and it computes you the effective rainfall. Then when we provide the type of crop and its planting date and harvesting date, then we have to provide the KC values, crop coefficient values, based on the initial development, mid-season, late season, and total. So these information you have to have prior of a particular crop, and on the basis of the rooting depth and other information, it calculates the. So here you can see the main factor which affect the KC. So it is all the climatic parameters and other things. Then you have to provide the soil type data also here. What is the total available soil moisture? What is the maximum infiltration rate? Then what is the maximum rooting depth? And what is the initial soil moisture at TAM? Total available moisture in percentage. So when you provide all this information, you are able to find out the how much crop water is required by the particular type of crop, and what is its irrigation requirement, and on the basis of that the irrigation scheduling is done and the water is being supplied to that particular field in the command area. So remote sensing is providing you the type of crop growth stage, what is the canal network in that particular command area. It is providing the rainfall. If you are having the rainfall, observed rainfall, it is okay. If you are not having the rainfall observed station in your command area, then nowadays the remote sensing based rainfall data is also provided, like FO data is there, then TRMM data is available at 0.25 degree, and lot sort of data is now available. Then soil map you can take from the NBSS LUP, which is in Nagpur, and FAO maps are also available. So you can get this information from these sources. So using this remote sensing data and geographical information system for your command area, you can find out. This is suppose you can see here it is a Landsat data of path and row 145, 43. Path means that is how it is flowing, moving from north to south pole, and what is the row, that is 43. So it is the path and row which pass over that particular area. So we select the imageries of our study area, and we have to keep in mind, we have to select those satellite imageries which are not having clouds, because it will distract the information which is behind that. We were not able to get the actual feature reflectance of that which is behind that cloud, because it will be giving the reflectance of the cloud. It can be done in the case of microwave remote sensing, because they are able to penetrate the clouds. But if you are going for the optical, you have to keep in mind that you select the data which is cloud free. Then otherwise, if you are selecting, then you have to go use image processing, you have to do again, it takes a time. So it is better to select the imagery which is cloud free. Then with the help of this Landsat, we are able to make the land use land cover map. What is the land use land cover of that particular catchment or basin? Then what is the soil map we can generate? What is the drainage network of that basin? And this, what is the canal network? What is the length? How is the distribution? And with the help of that, we are now able to calculate the how much area or the land use is under what. So we are able to get finally the statistics of type of crop, and on base of that we can manage our water which is there for the irrigation. So it is, you can see here, these are some of the imageries, remote sensing imageries, a part of Ganga Canal seen by satellite data. You can see how clearly you can visualize a canal. This is NDG, Northern Ganga Canal, which is going, and you can easily detect and visualize that this blue is a water body, because the reflectance of water is least, it appears to be darker in color. And with the, now here it is, again a river flowing here, Ganga river is flowing. So with the shape, again, there are different interpretation keys with the help of which we are able to identify the features on the surface. So this is also a water body and this is also a water body. With another element, we are able to see that it is a linear feature. This is straight and this is going zigzag. The course is like this. So we are able to identify this something is a linear feature which can be a canal. So it is based on your expertise, knowledge about the interpretation, you are able to identify that these both are river water bodies and this is a linear feature, so it can be a canal. So we are able to find the length of the canal and we are find the area under the this surface water body. So another thing it is seen that how you can, so this is from a IRIS panchromatic black and white image, image captured in a single band with a 5.8 meter resolution. You are identify the features. This is Cartosat data of 2.5 meter resolution. You are able to find this barrage. You are able to find these bridges. So all these information you can very easily see. So this is a Bhimgowda barrage. This is from the quick bird imagery of 0.65 meters resolution. You can very clearly find the length of this barrage. You can find how much this area in the submergence, like those all information which what about the catchment and the command you can extract using the remote sensing data. So it all up in the resolutions, whether it is a spatial resolution or a temporal resolution. I think there is a class basics of remote sensing. They will be telling you much in detail about this. So we are able to extract the information of the canals, water bodies, surface mapping. We can map all these. So this is how the branching is taking from the main canal. So these all information which are required for the irrigation management studies can be taken from the remote sensing data. So now I will be showing you a case study for a command area. The main objective of the study were to classify the major crops in a command which was a Ghat Parva command area and to obtain area under each crop using the multi-temporal satellite data, temporal at different time resolutions of satellite. So we were able to identify through the remote sensing which crop was in the command at particular time and what was its area, under how much area that crop was there using the multi-temporal satellite. Then to finally assess the crop water requirement using the crop water, crop wet and the GIS, which I have told you in the last few slides about the crop wet. Then to evaluate the irrigation on the base of this crop water requirement, it is computed that what is the requirement of a crop, of a particular crop in that command, and what is the irrigation requirement. Irrigation requirement we get after minusing the effective rainfall. So this much amount of water is required in this command area. So on the basis of that, the amount of water is released from the headworks, incorporating the various losses which may be due to conveyance losses, field losses. So that is being taken into account and the irrigation water is being calculated. Then finally we were able to do the scheduling for the command area, how much water at what interval of time and when to apply. So this really helped to conserve the water for that command area. Then with the help of this model, we were also analyzed various irrigation scenarios with varying crop. What if we take such crop, and if we sow it before or after with some time difference, what can be the scenario in that, how much irrigation water is requirement and what are the other statics. So that irrigation scenarios were generated by varying the cropping patterns. So the study command was Ghat Prabha left bank canal. It falls in the Karnataka at this coordinates, which is flanked by Krishna River, basing boundaries between Ghatprabha and Malprabha rivers, and West Maharashtra state. So the command area falls in the Belgaum and the Bagalkot districts of Karnataka states. So this is the study area map. You can see this is the Karnataka state, and this from this, and here it is our the command area. So this is our study area, command area, Ghatprabha command area. You can clearly see the network of canals. So these all information we extracted from the remote sensing data, the like drainage network, what is the command boundary, and all those information we did with the help of remote sensing using the GIS softwares. So in this study, to meet out our objectives, we used the IRS 1C 1D list 3 data of 9661, 9761 pathos of different time frames. Like this was at November, in 2000 November we took, then in February, then March and April. These were able to give the information of the crop, their growing stage, etc. Then the topographical data which we utilized were that Survey of India topo sheet as a base map to generate the our satellite data, georeferencing and other things. Then the meteorological data which we have used in this study was maximum and minimum temperature, maximum and this relative humidity, temperature, then rainfall, then wind speed, sunshine hours, then agriculture data, that is a crop calendar. When the what is the sowing date, what is the harvesting date, what is the total duration of that crop, and all this information we had from the land record departments, from the agriculture data from the land department. Then the soil information, what type of soil data is that, what is the soil moisture characteristics like field capacity and wilting point, and these all information were required for the study. So we used the IDRS. This is basically to identify the path and route of a particular satellite. Then radar imaging, I told, for image processing we have used this software. Then ArcGIS we have used for the digitizing the canal networks and basin boundary and other GIS works. The crop water model was used for computing the crop water requirements and the irrigation needs, and other informations in the Excel tools were done first, calculating statics. So the main methodology which we followed in this study was, first of all, the crop area, the crop acreage was calculated using the IRS list 3 satellite data. First of all, we georeferenced or georectified the images. Then, as our command area was coming in different satellite data, so it was in different tiles, basically we can say like that, it were in different tiles. So first of all, we georeferenced all the images. After that, all the images were mosaic, means they were stitched together. And after mosaicing, we subsetted our study area. Like in our case, it was a command area. So with the help of an tool, AOI tool, we were able to extract our study area. Means we have clipped out of the total imaging, we have clipped the area or subsetted the area which was for our concern. That was a command area. Then we generated the NDVI maps. NDVI maps were generated, that is the normalized difference vegetation index images were generated. NDVI basically is a indices to find the vegetation. So it is a combination, or we can say it is a ratio of infrared and red band. In infrared, the reflectance is very high, whereas in the red band, the reflectance is very less of the vegetation. So this NDVI, normalized difference vegetation index, was used to generate the NDVI image. And with that, we were able to classify the crop area and the non-crop area using the unsupervised classification. So now we were able to generate the maps of different time periods of how much area in a particular scene of an image was under the crop and what type of crop. So we finally extracted the crop area using the IRIS-LIS3 satellite data. Then with the help of the model, crop wet model, we were able to estimate the crop water requirements. So in that, first of all, as I told you, we need to calculate the reference evapotranspiration using the Penman-Montic method, which is very widely used method for calculating the reference evapotranspiration. And the basic inputs which are required for this method are rainfall, temperature, maximum, minimum, relative humidity, and solar radiation, sunshine hours, wind velocity, and all those information. And on the basis of these information, we were able to calculate the reference evapotranspiration. Then we computed the crop water requirements of major crops which were cultivated in the command area. And after that, we were able to calculate or estimate the net irrigation requirements. And on the basis of that, we computed the gross irrigation requirement. That is all again depending upon various efficiencies. Net irrigation requirement, then based on some of the irrigation efficiencies like conveyance losses, field losses, and all taking into account, we calculated the gross irrigation requirement for that command area. And on the basis of that, at canal intake, the water allowance, that is the rate at which water was allowed, was calculated. So this all estimation was done using the crop wet model developed by FDP. Then finally, we scheduled the irrigation. Like as I have already told, that the method which is normally followed is the basin flooding method for agriculture. But now we see that due to this, lot of losses are there. Losses in terms of evaporations, when water is standing in the fields or more water is there, then losses due to evaporation is more, than percolation losses are there, which are also leading to leaching and other things. So that method is not efficient. So now the efficient methods like drip irrigation, sprinklers are in use, which are there to increase the water use efficiency. And it is also a major objective under National Water Mission to improve the efficiency by 20%. So these latest techniques of estimation of crop water requirement and irrigation requirements, and thereafter doing the irrigation scheduling is very much in need in the time of today. So with the help of this, we scheduled the irrigation water which were computed using the model. So this is the base map of the Ghat Prabha left bank command. You can see this is the Hidkal dam site. This is Hukeri, and the water is being diverted to these canals to the whole command. So our target was to compute the irrigation water requirement, the water allowances which has to be released from here to the pond area. So the main flow, we can see the main methodology which we followed for this study, pilot study we can say, was divided into three. First of all, the satellite data. We downloaded all the satellite data, extracted the area, that the command area. Then from the Survey of India, we scanned, that was a hard sheet, we scanned it, made into digital form. We masked the catchment, and with the help of this catchment area, we extracted our study area. Then we classified the NDVI images, and from that we were able to identify the crop area and the non-crop area. Then with the help of this GIS overlay tool in GIS, we were able to identify the type of crop. Means we overlaid the satellite images of different time periods, like on monthly scale. And based on the crop calendar and other information, we identified what type of a crop was there in the land. And finally, we were able to find the crop application. Then the meteorological data was inputted to the crop wet model, and from there we computed the reference evapotranspiration. The cases values were taken from the literature. FAO literature is there, and based on some of the local information from the study area and providing the rainfall inputs, we computed this crop water requirement. And after the crop water requirement is computed, then giving the other input parameters like soil data, what was the rooting depth of those crops, and what was the scheduling criteria. Different scheduling criteria were there in the model. So based on that, we followed that if the soil moisture goes below 70% of the available soil moisture, it will ask for the irrigation. So on the basis of that, the irrigation scheduling was computed for the whole command area. So we were able to find out how much amount of water is required for how much area of crops under cultivation. So these are the different period images of the list data. Like we started from November, December, January, February, March. So all these are the images of different time periods. This is our command area, and these images, after being classified using the NDVI, as I told you that NDVI were generated, it is defined as the ratio of difference between the near infrared and red reflectance to their sum. So NDVI, that is the normalized difference vegetation index, is equal to the ratio of near infrared band minus red band. Why we have selected, I told you, is only near infrared band and red band, because the reflectance of vegetation in optical remote sensing, the reflectance of vegetation is highest in this band, and reflectance of vegetation in red band is very less. So we have taken the ratio of these and we have generated a indices for the images. So now, after generating the NDVI, which are ranging from -1 to 1. So now, from those images, index has been generated, which is ranging from a value from -1 to 1. And in this, the positive values, that is 0 and above, are towards the vegetable surfaces where soil was near 0. The values of the pixels which were near 0 were said to be a bare soil, and the negative values were open water feature. So from these images, now we have had an index number, and that define which is a pixel of vegetation. So the values which were positive, and analyzing different images and literature, we have defined a threshold value. Means if we are having a value around 0.4 or like that, it was a higher vegetation. So likewise, on the basis of this NDVI, we were able to identify the vegetated surfaces. Now, that model was prepared for this NDVI using the model maker in the ADAS images, and this helped to analyze our NDVI images which were generated. So NDVI images were generated using the model maker of the ADAS images, and unsupervised classification was used for that, and we were able to obtain the crop, non-crop on standard signature in multispectral data of different images at different time periods. So we used the images for November 2000, then January, February, March, April. So we were able to find the NDVI threshold values for these different images. So on that basis, we were able to find which areas are vegetation, and based on the literature and other information and the crop calendar, we were identifying the different features. So here you can see yellow is the canal, blue one is the river, black is the road, red is a crop, and the shine color is a non-crop. So you can see here. So on the basis of this, we were able to identify the different land use. So we were able to estimate the crop area. You can see here, crop discrimination and acreage estimation is based on the fact that each crop has a unique spectral signature. As I told you that every feature has a unique reflectance in remote sensing, and on that basis the reflectance are being recorded by the sensor, and we are able to identify the feature. Temporal images of the Rabi and season have negative and positive values reflecting the water bodies with negative values, as well as the greenness having the positive. So the greenness was towards the positive, as we have already seen in the last image. So these are the NDVI values which we have seen. So the classification of area into crop and non-crop for different months was done. This much area was under the cultivation, this during the different months in terms of hectares. Then statistics of overlay map used for computing the crop water requirement. Crop water requirement was computed, and with the help of GIS, we were able to find the command area, total area of the command area in this 2,96,987 hectares, while the total crop area was 1,48,457 hectares. So this all with the help of GIS and using the remote sensing data, we were able to identify these statistics. So using land use data, we were able to find this. This is the, in terms of hectares, the different crops like maize, meat, fodder, sugarcane, and the gross command area. So total crop was this much, and in percentage it is so given. So we can see from here that fallow and bare were almost 50%. So you can see almost here it is 50% of the total area. It is not under the cultivation. So this is the map which are showing you the different crops in the command areas. We can see the border. This is the non-crop area, and this is the sorghum, wheat, maize, and the sugarcane. So we can clearly get this information from this satellite data. And from this we can see here how much crop is under each, how much percentage of crop is under each type of crop. Major crop was 50. It is seen that 15% was under sugarcane, like that, and then fodder pulses we can say about around 9%. The most major part that was the fallow. So these all information you can very easily extract from this. Then reference evapotranspiration was calculated using the Penman method. You can clearly see from here that we use two methods, Penman method and the Thornwick method also. So Penman method method requires a lot of climatic data, as we can see that rainfall, temperature, climatic data, including solar radiation and other things are required. But Thornwick method, which is also taking into account only the temperature, is used for computing the ET, evapotranspiration. So this we have seen if we are using a Thornwick method and using the Penman, what was the major difference during those? And because the main is in many of the areas or the region we are having not all the data available for the required period. So some models method can be used in which data requirement is less, and this Thornwick method you can write in the simply in a program of Excel. So it is a less data requirement method with easily calculation the Excel. So you can see during this almost it is matching, and during this period it is the calculation through Penman PM method are pretty higher, and here higher. Then these are the crop water requirements which were calculated for monthly basis for different type of crops. So ET was basically the KC into ET0, and this ET0 takes into account the climatic factors, the temperature of the area, the rainfall of the area, and these take into climatic parameters. While this KC takes into account the soil and growing stages at different time stages. So these two takes into account the two sources. So total crop water requirement computed was for the sorghum, fodder, and sugarcane was computed, estimate like this. Then the maximum crop water requirement for is computed for the month of January, February, March is being plotted over here. And finally the irrigation water requirement was computed for the each crop and then for the command area. Separately for each crop was calculated, then for the command was calculated, and the total net irrigation and the water requirement for the whole command was there, and it was computed for the in terms of depth of water required for that command area for the irrigations. So you can see here that monthly NIR, that is near infrared net irrigation requirement into satellite drive coverage gives you the Ghat Prabha command area. So this statistics we have got from the command area of Ghat Prabha from the satellite drive crop acreage during that period. Then based on the field irrigation and gross irrigation requirements, as I told that the requirement of irrigation at different is having calculated because there are major losses conveyance losses, field losses, and all this, taking into account the net irrigation where for the field irrigation requirement were calculated and the gross irrigation requirement. And then finally, what water allowance at the canal head has to be released for the command area was calculated using the simple calculations on monthly scale. So this is the irrigation requirement, and we can see are higher in the months of December, January, and February in comparison to other months. So these were our results. So on the basis of these, an irrigation first irrigation required was computed. The total irrigation required we have shown here on the basis of the first irrigation, second irrigation, third irrigation, how much at what interval of water has to be supplied and how much water has to be supplied. So the total irrigation comes out to be each crop has been calculated. So finally, with the help of study, this study, we were able to use the remote sensing and GIS tools for the command area for irrigation water management, how the tools have created the spatial and temporal database and use the irrigation and can be used for the, has been used for the irrigation water management, and which is supportive for the proper planning and management of the water resource. Now the government of India is also saying that we need, we have to go for per drop more crop. So based on the assessment and estimation of these crop water requirements and irrigation water requirements, we will be able to properly plan the effective management of the water in our command areas. So with this, I am open for questions. Thank you very much.
Thank you, sir. Very informative and a lecture on irrigation water management and use of remote sensing and GIS in it. So I request all the participants, if you have any questions, you can either raise the hand or you can put your queries in the chat box. Okay, we have some time, so we can have question answer session, right? If you have questions, you can put in the chat box. Sir, whether these PPTs will be available to the...
Yes, yeah, I will provide.
Yes, sir. Yes. Sir, I wanted to ask one question with reference to this differentiating different crops. Using remote sensing, is it possible to differentiate all the crops with the help of remote sensing image?
Yeah, it is possible. As I told that we have converted into NDVI maps, normalized different vegetation index.
Okay.
Based on certain bands. As I told that NDVI is using near infrared and red band, because the reflectance is very much high in the NIR band and it is very too low in the red band. So the combination of that two bands, we create a ratio, and that ratio gives you a value between -1 and 1. So the values which are higher towards, say we can positive towards 0.3 or like that, based on the different analysis and the threshold, we are able to identify the vegetation. Okay. Now, based on the calendar of that particular area and information, we are able to use the overlay method, and we can identify what sort of a crop is that. So a lot of work has been done in this field by using the remote sensing data.
Okay. So there are some questions asked by participants. Yeah. Which method is convenient to measure evapotranspiration?
Evapotranspiration, basically, MODIS data is available. Moderate resolution satellite is there, MODIS. This data is available. From there, you can, using the Siebel equation, you can calculate the ET. Because at all the stations we are not having the ET data. Normally it is field instruments are there which can be used, but now the satellite is also providing you this product. Using the MODIS data, you can calculate the ET information.
Okay.
And this MODIS data is also freely available. You can download that data. It is having 36 bands, and these bands are used for different purposes. Like if we are going for irrigation or for calculating the evapotranspiration, so some band is specified. If you are going for like snow cover study, snow estimation, then band 31, 32. So different bands are used. So this MODIS data can be used for extracting the information of ET using the Siebel equation.
Okay. Then there's what is the somebody is asking what is the use of Microsoft Office in this study?
Some basic calculation as I told you that after computing the irrigation water requirement in the model, then calculating the allowances and other things, for that the Excel sheets were used, and the Foundweight method for calculating the ET was also written in the Excel sheet, because it is a simple the data is only temperature is required, and on that the program was written in the Excel, and we were able to calculate the ET. Otherwise, like Penman-Montes method, it is requiring very high data, all climatic data, and for that we use the crop wet model.
Okay. Okay. And I think, sir, which band data is useful for this study? I think that you have told.
Yeah.
Then
From if we are talking about the optical remote sensing, then the data from this list data and other, the near infrared and red band can be used for extracting the vegetation information.
Yes.
And you can also create the false FCC, false color composite, and in that you are able to identify the water bodies very easily. You can make the inventory, like if you want to digitize or extract the information of the canal network, so
Yes.
that you can digitize with the help of GIS software like ArcGIS.
This is Grishma from IMD. Rainfall data is not available for some area. What to do in this case?
Yeah. Like already I told in the slide that many command areas or the watersheds, the observatories are not there. Only one station there, or hardly there, maybe no station also, you can say. So in that case, nowadays, the satellite data from Aphrodite and TRMM, it is available, and that is free of cost. You can download, and that is graded data. Actually, we can see that is a graded data, and IMD is also providing you the graded data. So that grid data it is available at the scale of 0.25 degree centigrade. Okay, and temperature data is also available in graded form. So that data you can use for your study area. So this Aphrodite and this TRMM data, this is free of cost available. You can download from the website. But for the IMD data, you have to purchase that data. That is very economical for the research purpose or academic use. And that can be, once purchased, can be used, shared by many in the department.
Yes. Mr. Vasant Wagh is asking.
We have a, like I told that in the Himalayan areas, when we go for some data information, about 2000 meters, we are not having any observatory. So there comes these data, graded data from Aphrodite or TRMM are very useful. So we can use those data. The data is not for our study areas available.
Okay. There are some how to calculate the field capacity of soil. Vasant Wagh is asking.
Field capacity, there methods are there with the help of field capacity is basically when the soil is saturated. After the gravitational pull, it is the amount of pull. So tensiometer and other instruments are available in the soil laboratories. With that help, you can compute the field capacity.
Okay. Mr. Natarajan is asking, sir, whether we can do the same study with QGIS instead of ArcGIS, whether QGIS has many limitations compared to ArcGIS.
See, first I told you that ArcGIS is a paid software.
Yes.
And QGIS is a free open source software. So what I have feel, because I am also doing a lot of work in QGIS, but at some intervals there are some bugs, errors. Suddenly it may shut down or like that. But all work you can do in QGIS, there is no doubt. All creating all the layers and other things, watershed modeling, like creating the watershed boundary, drainage, and all that you can do in QGIS as well. All work can be done in the QGIS.
Yes. Okay.
The only limitation is that it is free software, and that sometimes it may suddenly shut down or have some. That is not in the case of ArcGIS and other things, other software.
Yes.
But recent versions have come of QGIS. They are still working very nicely. So a lot of work is being now conducted. I have also conducted a few training courses on QGIS and the DST and other sponsored programs. So it is working good. So a lot of work is being now done on QGIS software.
So I think, sir, there are no more questions. So, sir, I will take this opportunity to thank you on behalf of our institute and our department, and also on behalf of all the participants. I am very much thankful to you, sir, for sparing your valuable time and accepting our invitation and delivering sir.
Okay, thank you very much. Thank you,
Uh,
thank you very much, and thank you all the participants for listening patiently. And it is all due to Corona that we are not able to interact offline. But I prefer mostly offline trainings or lectures, because in that we are able to interact one to one. So
yes, sir.
yeah. So anyways, it was a nice session, well organized by Dr. Nimbalkar ji. Thank you very much to the institute, and especially
Okay.
to you for giving opportunity. Thank you very much.
Thank you, sir. Thank you. Okay. See, for all the participants, we have the next session sharp at 2:30. Please be there at 2:30 by Dr. Shamita Kumar. The next section will be there at 2:30.
3-3.5 रोटी लाया मैं और नहीं खाता था, लेकिन एक रोटी 1.5 रोटी छूट गई उससे, नहीं खा पा रहे थे।
हाँ मैडम.
येस
हाँ
बाजू निंबाळकर,
हाँ
गुड आफ्टरनून.
हाँ गुड आफ्टरनून मॅडम. हां तुम्हाला मी आता प्रेझेंटर केलेलं आहे.
ओके.
हां आणि अजून मला वाटतं आता 2:30ला अजून किती वेळ 5-7 मिनिटं आहेत मला वाटतं. हां
हो हो हो
हां
ठीक आहे.
5-10 मिनिटं
सो
आहेत. मग
whenever you
आपण
say yeah,
हां
I'm ready.
हां
Whenever
हां
you जेव्हा म्हणाल I can start.
हो चालेल. मी आधी
Okay.
इंट्रोड्यूस करतो आणि मग आपण
Okay.
स्टार्ट
Fine.
करू. म्हणजे 2:30ला
Okay.
अजून म्हणजे आता तो कमीच लोक आहेत आता. अजून येतील
Okay.
म्हणजे
ठीक आहे
70-80
ठीक
लोक असतात. हां
राईट नो
हां
प्रॉब्लेम.
ओके मॅडम. हां
अब जितने भी जो सब्जेक्ट जो वाइवा लिया है या प्रोजेक्ट लिया है, उन सब में एग्जाम शीट नंबर डाल, मार्कशीट में ही चीजें फिल कर देना आपको.
Hello, good afternoon, everyone. Now we will be starting with the last session for this today's FDP program. So now for this session, we have Dr. Shamita Kumar. She will be, so I'll introduce Madam. Dr. Shamita Kumar is currently Professor and Vice Principal at the Institute of Environment Education and Research, Bharati Vidyapeeth Deemed University, Pune. A landscape ecologist by training, she first started using geospatial technologies in her work biodiversity conservation almost 20 years ago before moving full-fledged into advanced geospatial technologies. She is a member of National Geospatial DST.
Nimbalkar sir, I can't hear you.
Unmute. Okay. Madam, can you hear now?
I can hear you now, yeah.
Okay. So I'll start again. Madam, welcome, madam. So
Thank you.
I will introduce Shamita, madam. Dr. Shamita Kumar is currently professor and vice principal at the Institute of Environment, uh, Environment Education and Research, Bharati Vidyapeeth Deemed University, Pune. A landscape ecologist by training, she first started using geospatial technologies in her work biodiversity conservation almost 20 years ago before moving full-fledged into advanced geospatial technologies. She is a member of the National Geospatial Capacity Building Committee of the Department of Science and Technology, Government of India since 2012 till date. She she held the chairmanship of the committee from 2016 to 2020 as part of DST's initiative. She, along with her team at Bharati Vidyapeeth University, has set up the portal DST iGate, which is a one-stop portal for the National Geospatial Capacity Building Program. She is a Fulbright Nehru Scholar and is a guest faculty of University of Cologne, Germany through a DAD fellowship since 2013 till date. She is a member of Executive Committee of Maharashtra State Forest Academy and she has numerous publications and books to her credit. Okay. Also, I will tell you that they are at the Bharati Vidyapeeth Environment Institute. They are running this program on MSc Geoinformatics. So, Madam is there. So, I will request Madam. Madam will be delivering a session on basics of GIS and the various data sources and softwares. So I will request Madam to continue with his session. Thank you.
Thank you, Dr. Nimbalkar. Good afternoon, everybody. It's a real pleasure to talk to you. I was told that the participants have come from all across India. And in spite of the other things that the pandemic brings, I think this is a real opportunity that we have in the field of education that this digital technology enables a wide reach. Post-lunch sessions are always very difficult sessions. Even normally they are very difficult, but more so in the digital era, because you really don't know whether somebody is listening to you or, has dozed off. And of course, all of us have numerous anecdotes about it. And I would just like to begin by telling one about my daughter. She was actually writing an exam, and the invigilator was there. And after some time, they hear this very funny noise coming, and they realize that the invigilator was asleep. So, yeah, well, I hope.
मैडम आवाज मैडम
Madam,
आवाज
uh, काय झालं?
To raise your hand, anybody, if you have already worked with remote sensing and GIS. Just raise your hand so that I know how many of you are actually familiar with this technology. Okay. So few hands are up, yeah. Okay, so this is just that I know at what level I can pitch my talk. So I've just saw about 4 or 5 hands on, so which means I can start from the base. All right. So let me share my screen. So is my screen visible to all? Nimbalkar sir?
Yes, madam, it is visible.
Right. Thank you so much. Okay, so geospatial technologies, I call it the eye in the sky, and so do a lot of people, because it's wonderful to have this eye in the sky that sees things that we do not actually see, and enables us to use what it sees, in the different kinds of analysis that we do. We would have never known that the earth looks like this, if we didn't have the ability to go up there and see through this this kind of technology that today enables us to visualize what our beautiful earth really looks like. This is a very interesting picture. If I give you a clue, I'm sure you'll know, but without a clue, can you really tell me what this is? What do you think this is? It's sort of a land bridge. Yes, it's a land bridge between India and Sri Lanka. So it was in the news about 15 years or so, when people through satellite remote sensing actually found that Ram Setu, as we know from mythology, is something that you can actually see with remote sensing. So the question this raises to my mind is, did Valmiki already know about the existence of Ram Setu? Or did he use places and events that were there during that time, as we see that Ramayana is replete with, incorporated into his, epic story? So this is a question I think only he can answer. But these are the kind of questions, very interesting questions, that remote sensing throws up, because it helps us to develop this very different perspective on things. So I guess we will never know whether Ram Setu existed or, Ram Setu was built, as we know, through the Ramayana. We don't know about that. With remote sensing, like I called it, the eye in the sky. So which means it helps us to see things that we normally do not. So you see this picture over here, and it seems as if a stream of smoke, is coming from a mountain. But if I just change this, it's the same picture. It's the same picture that is seen through different eyes. So the first one that you see is a band combination of band 1, 2, and 3 of the Landsat satellite image. And this one is a combination of band 4, 5, and 6, with 6 being the thermal band. in this Landsat remote sensing satellite. So our normal eyes just see the smoke, but when you see it through the eyes of the satellite, you are able to see a different picture. And this enables you to just sit at your desk and analyze, let's say, forest fires or any other thing that you really cannot, see with your eyes. So this is what makes it extremely fascinating. In fact, there are a lot of citizen science programs where NASA especially gives tons of images free, asking people to see what they can find. And this exercise has led to some very innovative discoveries, across the earth, something that people never knew existed. So this is really the power of, remote sensing. And I believe you have a remote sensing class somewhere in the week. So I won't dwell much more on this, but this is one of the data sources that we use when we use GIS analysis. So I think you all are familiar with the term GIS and have heard about it, and that's why you are here. So what is really this geographical information systems? It's an information system that uses geography, uses location. And as you can see here in this particular picture, the data from the real world is extracted in different files. And each of these files or layers, as we call it, just caters to one type of data. So if the real world is what you see below, then your land use, land cover is extracted. And as you can see, it's called as raster here. That's a raster data type. Then you have elevation, which is also a raster. You have land parcels, which can be, as you can see here, a vector data file, streets, customers, electric lines, so on and so forth. The principle is that a single data file is in a single layer. So a layer can never have multiple data files. It has to only have a single data file. And that's what we do. So it's like, putting all these trace paper sheets together and then seeing it from the top through which you have a whole picture. And the fact that the data is in layers allows you to fire certain queries to get certain answers. So it's really interesting, when you start playing with this, you can sit for a whole day in 24 hours and keep playing with this. So very often you have this terms, GIS, geomatics, geoinformatics, geospatial technologies. So while they are very often used sort of synonymously with each other, there is differences. There are differences, in them. So if you look at geomatics, it more deals with geodesy, that is the shape and measurement of the earth, and mathematics and engineering. So that's geomatics. You look at geoinformatics, it's basically a combination of geospatial technologies, GIS, that's geographical analysis, as also is information science. So it is an amalgamation of all these three. And if I take it further today, then geospatial technologies itself is a combination of remote sensing, the system, the geographical information system that we use to input the data, and also data that we are getting from our satellite navigation systems, which is basically the locational data. So about 5 to 7 years ago, I would stop at this and say, okay, this is what geospatial technologies is all about. But today, if you look at it, it's much more than this. So it integrates with the sensors, Internet of Things. It integrates with big data. We have big geospatial data. It's very much part of, IT. So earlier you had these fields, IT here and geospatial technologies here. But now this is, geospatial technologies is very much embedded within the IT sector. And of course, artificial intelligence. So the whole field, has changed from what it traditionally was about 7 to 8 years ago, very, very massively. And this means that our traditional data sources and our traditional analysis techniques have also changed over the years and are continuously evolving with the evolution of IT and IT platforms as well. And this is, again, what makes this extremely challenging. So this is the only slide I have about remote sensing, since you have another session on this. So just to explain to you what remote sensing does, it basically uses electromagnetic radiations. It measures emitted, absorbed electromagnetic radiations to create the satellite images that we actually analyze and use in our various applications. So there are numerous satellites, which are there. In fact, I think we have a lot of junk out there in space as well. So if you look at the global satellite observation systems, there are several countries that have launched their own satellites. And I think with pride, we can really say that this is one of the technologies that India leads in. So with all our space missions, we also carry foreign payloads, that is foreign instruments on our satellite missions, which show the confidence that other countries have in our satellite mission. I think it's really a moment of pride for India. To see that we've come a long way from INSAT 1B, which used to give us, or which gives us, weather forecast. So we have a host of satellites that we have launched, and much more in the recent years to Mars and the moon, as well, which give us a large amount of data that is used in various government applications across various departments. Satellite images, they come in all shapes, size, and colors, right? If you look at the earlier ones, they had a spatial resolution of 500 meters, which means that every 500 meters, whatever dominant feature is there is captured. And you lose the ones, which are not really dominant, because the pixels, they go by the majority rule. And over a period of time, this has now come down actually to less than 1 centimeter, sub-centimeter level. So we even have those kind of satellites that give us sub-centimeter level, images. So which means that you can see the number plate of a car, you can see the pen on a table, all of this can actually be seen, right? And this is also one of the technologies that was used to capture Osama bin Laden. So along with field surveillance, the US heavily relied on satellite surveillance, where they were actually able to make out that somebody of the height of Osama bin Laden used to, walk on his terrace. So there's a special technique through which that is done. And combining this intelligence, they were actually able to, capture him as well. So if you look at this here, you can see that the signatures are different. I don't know if you can see my mouse. There's this dense urbanized area, and you can see the signature. Similarly, if you look at some place here, you can see just normal, not a dense urbanized area. You can see agriculture areas, and you can see a lot of agriculture fields, which we know because of the shape and the size. So okay, this is a crop which is present. So red means vegetation is present, because that's a false color composite, since vegetation always reflects better in the near infrared part of the electromagnetic spectrum. Vegetation always seems red. And we can actually differentiate the health of the vegetation better in the near infrared range. So all that you see is agriculture, current agriculture. You can see fallow land, because I can see that there's no moisture. So this would be a 30 by 30 meter pixel, yeah. So this is like standard normal Landsat imagery. US satellite, would have this kind of a resolution. Even our Indian List 3 satellite also gives us this kind of resolution. And Earth observation can really be done at different scales. So I can have it, like I told you, at the scale of 1 centimeter or sub-centimeter level, or I can have sub-meter level, not centimeter, sub-meter level, and I can also have it at a global scale. This is also a very interesting satellite image, because this is a night light image, and this particular image, it captures light which is emitted from regions across the world. And there's an interesting research, and we use it quite often. We use this nightlight data as a surrogate for economic activity. So it's used as a measure of GDP, because GDP is a data which we do not get real time. But the satellite images, we can get them real time. And it's a wonderful way of using this as a substitute for GDP, which can be used in, in various different kinds of analysis. So you can have this from small scale to large scale. All this kind of satellites today are available. And unlike literally 10 years ago, when acquiring satellite data was very, very tedious, I remember filling out the forms for ISRO. I needed about 3-4 permissions, deposit the money in a bank, in an account, send it to them. It's so easy now. I mean, I don't even need anything of that kind. There are tons of images of very good quality that can be downloaded for free. So in the last 10 years, there's been a huge jump in what this technology can do and what kind of platform, software, and data are really available. This is one of my favorite pictures because during my thesis, almost 20 years ago, I struggled with actually counting black buck in one of the sanctuaries here, and we wanted to see, how these numbers have dwindled. But this is a GOI satellite which has a resolution of 0.5 meters. Every 0.5 meter is captured on the ground, and you can actually count these individual wildebeest here. So this is wildebeest migrating in Africa. And this satellite actually enables you to count the individual animals, doing away with the need for doing census, because this is the most accurate census data that you can ever get. Or you need teams of hundreds, who are going out there and, counting the animals. So just to give you a sense of what I mean is, I'm sure you're all familiar with the electromagnetic spectrum. And this little thing that you see here, 0.4 to 0.7, this is our visible range. So our eyes are able to see only in this range. We do not see in this range or in this range. But satellites, they help us to see in this range. And so we can see plant stress, we can see minerals, we can see rocks, we can see, identify soil types. There's so many different things that we can see through the satellites and integrate it, within our own analysis. So this is the reason, the eye in the sky, because I think it really helps us to see what we can't see. And as human beings, we feel, I can see everything around me. But actually, there's so much that we cannot see, which is just limited by our own vision of being able to see between 0.4 and 0.7. So it's always fascinating to see through the eye of the satellite. This is another instrument. It's a Tom's image, which actually captures carbon dioxide concentrations across the globe. Imagine that you had to do this kind of study manually. I mean, you would need countries to cooperate. You would need teams in thousands actually measuring this. And there's always scope for human error in this. But with this particular instrument, you are able to measure carbon dioxide concentrations directly from the satellite. So, and then produce this kind of image. So it's accurate. There's no scope of error. It's far much cheaper to pick up these kind of things. And this is also when the ozone hole was established, without a doubt, when we had this kind of data coming in. And as you can see here, from 1979 to 2010, it's really increased. And this is also measurement through satellites where we know exactly where the ozone hole is. This is a very interesting application. And so just to tell you that it's not only used for high-end applications and atmospheric measurements, but also something like this. And although this is an image by NASA, I have seen a similar system work on the eastern coast of India in Orissa, where the local fisherman, he goes to a shack which is on the beach, and he asks a person there, where should I go today with my boat? So the person looks up the screen and pulls up an image like this, and then he tells him where to go. What he really has with him is satellite images that give the plankton density. He doesn't see fishes, of course. You can see fishes, but not with this technology. But he doesn't see this. What he sees is plankton. So if you look at the left-hand side image where my cursor is, this is the temperature of the water. So you can see from the coastline as we're moving inwards. And here you can see that this is plankton density. So wherever you have dense plankton blooms, this is where the fishes are. And this is where the fisherman is guided so that he does not have to spend days at sea, but can go in and go eat and get out quickly with his catch. So it's actually used on the ground, to better people's lives, right down to that level where we think, okay, what can geospatial, technologies do? So all you need is an image that tells you what it is. Over this week, I think you're going to hear a lot of applications related to water resource engineering. But as you can see, the use of GIS is only limited by one's imagination. Whatever problem has got a location associated with it, that's where GIS can be used. So that's it. If you have a location, GIS can be used. So whether you look at watershed analysis, resource inventories, land management, tax purposes, network analysis, planning better roads, corridors, mapping hotspots of diseases. It's been widely used in COVID. Selection of corridors, transport corridors, wildlife corridors, logistics routing. Everybody uses the GNSS chips now. Facility management, big thing in India also at the moment. Spread and diffusion of diseases, emergency health services, a lot of engineering design, site selection for solid waste, for wind farms, for solar farms, all of this. You can just think of it, and this application, can be used there. So this is a very nice application. It actually tells us the extent of solar irradiation, and this is a very useful analysis to actually plan solar panels over buildings. So with India, with its huge thrust on increasing its solar capacity, these kind of technologies and this kind of data really comes to the fore, where you can actually use the data very, very effectively for effective planning of placing of solar panels. Wind farms, it's widely used in the wind farm industry as well as in the solar industry. So using a couple of parameters, for example, elevation, land use, land cover pattern, roads, proximity to towns, the wind speed, you can easily decide which is the best place where I want to set up my wind farm. So all wind farms company, like I said, they use this kind of technology, and we call this as habitat suitability. So this is, it's quite old now, and it's used quite widely. So with the increased availability of very accurate location, which is also actually a very recent phenomena, I would say about 10 years or so, again, there's been a proliferation of a host of location-based services. So this is a common phenomena that we call as geofencing. So if you've experienced this, you can walk into the perimeter of a mall, and if you're already registered with one store or the other, they know that you are in, and immediately the promotional messages, start coming. But also the fact that India has launched its own satellite navigation system, and we also have our own what is called as a wide area augmentation system, which is called as Gagan, which means that we have location DGPS kind of systems, at places across India that increases the locational accuracy on your cell phone. So cell phones today are also a very good substitute for, let's say, student work for location. So earlier, of course, you needed to have those GPS systems. It's actually called as GNSS now, but I'm also old school, so GPS comes more easily to me. But it's GNSS now, because GPS is an American satellite, and the term GPS was used when no other countries had satellites. But today, India has the IRNSS, China has Baidu, Europe has Galileo, and Russia has GLONASS. So we no longer call it as GPS, actually, it's GNSS. But like I said, I'm old school, so that's how it comes to me. So even with a mobile and with a single app now, we use an app called as GPS Essentials. You are able to get very, very accurate locations, which is really good enough for student projects or any of the faculty projects. But sub-meter level accuracy or sub-meter level accuracy is something you'd definitely need a DGPS, but it's still good enough. And that also shows the advancement in this technology. If you really recall, I recall this very clearly. About 5 to 6 years ago, when I used to order a Ola or a Uber, the driver used to tell me कि मैडम मैं आपके जगह पहुंच गया हूं, and I used to tell him आप पहुंचे नहीं हो, मैं बाहर खड़ी हूं, because we didn't have this locational information very fine tuned. But today, when you're standing for a Uber, he comes very, very close to you. So this shows that there's an accuracy in locational information, and he actually knows where you are. So Amazon or Zomato or all of these services, they've just made it's a huge business just by the locational technology itself. And again, this is an interesting part of the technology. So GIS or geospatial technologies, they can basically answer these questions. The most simplest is location. Where is something? What is the condition of that particular thing? We can also look at trends. What has changed since 1980? So this kind of change analysis is possible. Patterns. Is it clustered? Are diseases clustered in a particular place? Are they spread out? Is the soil contaminated in a particular place? Is there a water shortage? So all these kind of patterns also can be extracted. And at the highest level, of course, is modeling. So using the data of the past, to model the future. So climate change in the past for the future, merging it with water conditions, seeing what they are, and can you predict it for the future, and so on. So there are a lot of questions that GIS can answer. I thought that I'll just put a few steps, about the basics, just in case somebody is completely new to this. So, for example, if you have a tree, in a normal position, you can describe this tree in two ways. One way is you can say, okay, this is a species, the height is so much, the age is so much, and the condition is good. But if I have to put or use this information in a GIS system, then I need something else. And that something else is location. So the minute I'm adding location to my normal standard attribute data, I've got GIS data, right? So this means now my data is compatible for all kinds of GIS analysis. So the GIS software, as you can see here, it basically links the attribute. So for example, you have a parcel here, and this land parcel may have 100 different variables. So the GIS system, it links your database to your spatial data. This is the spatial data as we call it. And this allows you to fire queries, allows you to model, allows you to do a trend change analysis, and so on and so forth. So A, we need to have this, and B, you need to have this. So basically, this is the data that you need. So when you look at this over here, you have different types of data which are represented in each different layers. So with each layer, it is linked to its own attribute table. And if you see here, I've purposely put down 3 different sort of symbologies. So this is a point. This is sort of
Madam, you are not audible.
same location to enable me to make an analysis. And now this tells me that the very basic GIS data types are basically this, that's it, right? So we look into this a little later, but simply put, this is what the basic GIS types are. So I have location data and vector or raster. So vector is basically a point, a line, and a polygon, like I showed you. A raster is an image, it's a grid, so that's a satellite image. So that's basically what a raster is, and I have attribute data. So a couple of years ago, again, I used to stop here and say, okay, this is all the data that we have in GIS, and it's so simple and we can do it. But as we will see this today, it's, the story has really changed. But yes, at the basic level, this is what the data is. You have vector data, raster data, and attribute data, which means that everything that you see around the earth has to be either an image or a point line or a polygon, right? So how do you decide the data type? For example, Pune is a city, and should I show this Pune city as a point, or should I show Pune city as a polygon? Because it can be shown as both, and that depends upon the scale. So before I start to work with my data, I need to be sure of the kind of data type I want to use, because this can't be changed midway. So if I'm working on a problem at the scale of Pune, obviously Pune is going to be a polygon. And if I'm going to work with Pune or at an all India level, Pune is going to be a point, right? So it depends upon the scale and it depends upon the analysis, which means that I need to think beforehand of what is the kind of data representation that I want to use, because it can't be changed midway to whatever you want to. The second thing that comes about, which is really very, very important, is that the Earth is round. That's what we assume. And we have latitudes and longitudes on it. So we know the exact position on the Earth. And on this round surface, we are able to make measurements. But the question is, can we really make measurements on this Earth? Because we don't carry a globe with us everywhere. We are always making measurements on a topo sheet, or we are always, when we put it onto the screen, it's a flat sheet. So how does this work? How does the same measurement of latitude and longitude actually work when you make the Earth flat? Because if you don't get past this problem, we can never make any measurements on the surface of the Earth. And the fact that the Earth was round was thought until Newton came in with his theory of gravity. And we now know that the Earth actually looks like this. And now this makes it even more difficult, because if it was a round Earth, it's easy. I mean, I'm sure a lot of you are surveyors and you already understand these concepts. So how do you make measurements on this? So we theoretically call this a geoid. So how do you make measurements on a surface like this, where you need to understand again by making it flat? Whenever we measure, as you know, we always need a starting point, right? So if I say I'm 5'4", obviously I'm from the ground, 5'4", not on top of the table, and that's my datum. That's my starting point, which I say. So the starting point for making measurements on the Earth's surface is what we call as a datum. And if we have a body, like this, right? The Earth, which you can see like this, if I have a starting point, obviously this difference and this difference is going to matter, right? So I need to have something where I'm trying to make this irregular surface sort of smoothen it by fitting it with an ellipsoid. It's a mathematical formula, or approximation, or in simple terms, when I try to explain is, you take a stone or a irregular shaped ball and try to fit it with like something like a swimming cap, which sits very tight over it, but smoothens the surface so you don't see the irregularities. And then on the smoothened surface, it's very easy for me to make the measurements. So that's what an ellipsoid does. So we use different kinds of ellipsoid so that we can make measurements on the surface of this Earth, which has got this highly irregular shape. I'm sure you have heard the term WGS 84, because all your GPSs, if you use GNSS, they all use this WGS 84, right? The World Geodetic System 84. Now, WGS is basically a universal datum, where you have something where the entire Earth is fitted with one particular ellipsoid, something that you can see here. So normally every country has its own ellipsoid, which means basically they are trying to pull the cap towards their side, because then their part of the world becomes smooth and they can make measurements there. But then measurements made here are not compatible with some other country somewhere. And so there can never be global cooperation. But what we're looking for is, something like this, where you have a uniform ellipsoid that fits the Earth so that you have a common datum. So very often in your positioning systems, the GNSS, we use the WGS 84 ellipsoid and the WGS 84 datum, which is the universal datum. And what happens if you use the datums differently? Then what you get is something like this, where if you try to join two sheets, they will not join to each other, simply because the starting point of these sheets is very different, right? So you can see this is WGS 84, this is NAT 27, and this will never match. This actually should have fitted here together. So these are some common errors when you begin with, when you're beginning to learn, because the concept of the datum and the projection needs to be very clear. It's a very simple concept, but one needs to understand this when one starts to work with data. The next is, once we know the starting point, the next is we need to make our round Earth flat, because we cannot make measurements on our round Earth. And when we make our round Earth flat, it becomes like this. So 2 points that were very close to each other, they can move far apart. So obviously, how do I make measurements? Here it was fine, there were latitudes and longitudes. But when I cut it open, the latitudes and longitudes, are all gone. So I need to project this in such a manner that any graticule, that is the latitudes and longitudes that are placed over it, they have sort of a square grid or measurements can be made. So this is a mathematical exercise where we put the earth through various different shapes or what we call as developable surfaces. So this is a plate, this is a cylinder, and this is a cone. So you can also use it in different orientation. You can have it here, or even oblique. And what this does, it helps us to make very accurate measurements over small areas of the earth. So projections, needs a week actually to go through, but I'm trying to explain it to you in 2 minutes. So just I'm going to give you a simple example. So imagine this is your earth, and imagine I have my light source here because I want to draw the latitude and longitude onto a sheet of paper. And around this globe, I have wrapped this sheet of paper. So obviously I've now got my latitudes and longitudes, my grid on my paper, and I'm opening it out. Now, if you open this out, you will see a very interesting phenomena. You will see that in the central part over here, the grids are a square. But as we move towards the poles, the one side of it is increasing, which means that the area is increasing. And therefore, by using a projection, I can only make some part of the earth into a square grid, and this is the part where I want to make the measurements. So I'm just going to go back a bit, and this is why you have these different orientations. Because in this globe, maybe I can make this part a square grid. Over here, I can make this part a square grid. Over here, a very small area where the plate touches the globe can be made a square grid. Here, this is very good for regions like India. So, which is not on the equator. So I can make this area a square grid. So all of these different mathematical calculations, they are such so that, we can make measurements on the surface of the earth. Now, if I don't understand this and I just use it as it is, what I will get is this. So this is a distortion that comes from the cylindrical projection where Africa and Greenland are of the same size. In reality, Africa and Greenland are like this. And because there you saw that there was a distortion towards the poles, Greenland increased, right? And therefore, I must understand this concept of projection because I need to make the 3D Earth into 2D. And when I make it 2D, there are going to be distortions. And how do I deal with these distortions? So an understanding of projections is extremely essential as to in which system do you actually project your data. Some of the most common ones which are used in India are this, that is Lambert conformal conic. So if you're working at a national level, one uses a Lambert conformal conic or a polyconic projection. Survey of India, in all its older topo sheets, they use a polyconic projection. Recently, they've started using UTM projections, but India is divided into various zones. So UTM projection cannot be used for the whole of India. It's different for Maharashtra. The zone number is different for Maharashtra, for Madhya Pradesh and Chhattisgarh, and so on and so forth. But at least you need to have an idea, okay, that the data must be projected before you actually begin to use it in your analysis. So once you've got the data ready, this is where the exciting part actually begins, is you move on to spatial analysis. And here, this particular analysis, it turns all your raw data into information, providing you rich insights into what is actually there. So, yes. So it reveals patterns. So at this stage, we apply statistics, we apply interpolation, we apply a lot of spatial analysis tools to actually extract this information to see the different patterns that exist in our data. I'm quite fascinated with this because this is something that Hippocrates stated in 400 BC, and it is so relevant to us today. And if you just take about 30 seconds, to read this, he says that whoever wishes to investigate medicine should actually look at where the person is working and where the person actually lives, because all this is going to play an important role in determining what disease he has. So for somebody 400 years ago to actually think of that location really matters, is quite fascinating, and understanding the importance of location in spatial analysis. So in spatial analysis, basically, I've just tried to put down 3 broad categories of analysis that we do. One is visualization. So which means you can keep showing interesting patterns, right? So using all the principles of map making, you are able to show interesting patterns. High economy area, low economy, high pollution area, medium pollution, low pollution, air pollution areas, or bad water quality, good water quality. So this kind of patterns is possible for us to show. And the other one, the next one is where we apply statistical techniques to actually pull out more interesting data. So whenever you do, for example, like a cluster analysis, I can see that, okay, this particular locality has got a lot of patients. But what I can't see is, why does this locality have a lot of patients? Then to understand that, I need to understand the underlying data, and I need to analyze that, which is what is the water there, what is the kind of housing they have there. And when you analyze the underlying causes, through statistical methods, we call it as a hotspot analysis. So cluster analysis just tells us that there's a cluster, but hotspot analysis tells us why is there a cluster. And this is very often important in finding a solution to the problem. And the next one is, of course, explaining the patterns. This is where you use modeling, regression, and other advanced spatial techniques, where you actually model the future based on your past data and try to explain, what's going on there. So this is, at a much higher level when we use all of these tools. So that is the one part, that is, I would say, the old way that we did GIS. And of course, we still teach that to students and so forth. But GIS has come a really long way from what we have, just seen. So before I go on to that, I would like to just briefly talk about software, because there are two things that when you're working or when you're learning GIS, you need. One is the software and one is the data. And again, about 10 years ago or so, why 10 years? I think even 8 years ago or so, software is extremely, extremely expensive. And this is one of the reasons, I think, why it's not being introduced across the country, as much as it should be, because a report of the Geospatial Task Force Committee of the Human Resource Development Ministry in 2013 highlights the immense lacunae that is there in geospatial professionals across India. So we do not really have the numbers to actually meet the demand. And colleges do not teach this because of the exorbitant price of the software, and also the lack of data, because you need data to teach, and data is not really available in the open domain. But this has changed over the last 5 to 6 years. This has really changed. So since this is a workshop where you're looking at water resource engineering and GIS, I thought that one can talk about this. I've used this personally and have several publications on this. A very, very useful open source tool, which is a soil water assessment tool that's used to simulate both the quality and the quantity of surface as well as groundwater as a result of various land use, land cover changes. So it can also be used to model future water existence, in basins. We've used this quite extensively in the Mulchi region here, actually simulating land use, land cover changes on the Mulchi Lake, understanding what kind of management the Tatas need to manage their own lake, which they use for hydroelectricity generation. So this is something that you can explore, completely open source, completely free, and has got not only data, but it has got a chapter-wise, I would say, a manual that actually takes you through this entire process of how you can, do this. So PhD thesis can definitely come about, without any help, by just looking at, what's out here by itself. The one that I really frequently use very, very often is QGIS, and QGIS has come a long way since it was, first released. It is very, very rich today in terms of modules or plugins, as we call it, to do any kind of super analysis as well. So you compare it to the most popular software on the market, commercial software, which is ArcGIS. It does almost everything that a student or a teacher needs, for research. Of course, commercial softwares have their own benefit and they're far more simpler user. They have a lot of help associated with it and they're smoother. It's like driving a BMW, versus whatever car. But this has come a long way and it's really quite smooth today. So that is for GIS, and this one is for remote sensing. So if you want to analyze satellite images, this is a very, very robust software. It has strong algorithms. I would say comparable to the commercial softwares. We have the commercial equivalent would be ERDAS Imagine or would be Idrisi, which are popularly used. So this is extremely robust and today very, very simple to use as well. So it's completely free and both of them are fairly user-friendly today. Today, we also use open source software for analyzing geospatial big data. And I'll come to that in a bit, but GeoPandas is again Python-based, and we use this extremely widely for analyzing geospatial big data. So this is again I think a key tool that's used in most programs today. This is a tool, again, very, very useful, of the European Space Agency. And I'm always quite amazed at, what these space agencies do and what India can't do. India has had a space program for almost 20 years now. The European Space Agency program is fairly new, I think hardly 6 years old or so. But the kind of educational material that they have made available to students and the kind of opportunities that they give is very amazing. So I had a student from Bhutan. He was deputed and he worked with the geological survey there. And we were looking at displacement of the Bhutan Himalayas. And the kind of images that we were analyzing, needed high computing power. We wrote to the ESA, and I think within a week we received a response with a key that allowed him to access, their server and work with his images, which made analysis like a breeze. But we don't still have that here, and this is, I think, when we really need to progress much further. So Sentinel, the European Space Agency, has these Sentinel images. I'll come to that in a bit. But they have also here, as you can see, the toolbox. So you don't need any software. It's like, software as a service. You can just use it directly from the cloud here. You can use their images and you can directly do the analysis. You just need to use your computer. You're using their computing power. So this is fantastic. I mean, there are all kinds of images, from microwave images to multispectral images to high resolution images as well, which are available from this site. This is another very robust one which I've used, and this is extremely good for analyzing very high resolution images. So I showed you the pixels and I showed you how an urban dense area differs from a medium dense area. But let's say you have a satellite image with 0.5 meter resolution, where you can see this individual field or individual pen as well. The computing power required is quite high and the algorithms are different. So we call this kind of analysis as an object-oriented analysis. And this Orfeo toolbox, allows us to do object-oriented analysis. And again, this is new because these kind of resolution was not available earlier, but now it is. And the commercial software, which is equivalent with this, is we can use NV. Yeah, but again, there's a cost to it. So how many softwares should a college buy? Yeah, but this allows us to, very easily analyze high resolution images through object-oriented segmentation. This is another white box tools, and these are extremely good for, as you can see here, geomorphometry and hydrogeomatics, but also for LiDAR. So LiDAR data can be again used very well. So all of this you can see they have tutorials and they have data. So anybody who wants to learn GIS, you can just learn it without spending much. So this is Ilvis. Ilvis is another very popular software. I don't use this often because I like the interface of QGIS much better, but it can perform the same functions that QGIS does. And it's much older. It's about 30 years old, I think, if I'm not mistaken. And today it has a certain degree of user friendliness, but you know how it is with software. Once you're familiar with something, one wants to use it. So yeah, that is really the sum. There are many more, but this is really the sum of the most user-friendly ones, you know, that I have put across. So that tomorrow, if you want to start learning on your own, you know, these are some of the ones that I would highly recommend that you use. And now we come to data sources, because you may have the software, but what if you don't have the data? And the data is really the most time-consuming part of working with geospatial technologies. And fortunately for us, we have an extremely large number of data sources that are available. So this is natural earth data. I think, you know, you take almost about
Madam, you are not audible.
this is, sorry.
Now you are audible.
Okay, so did you lose much or?
No, for some time, half a minute,
Okay.
some 30 seconds, maybe
Okay.
30 seconds.
All right. So this, I'm just going back to this. So this is the natural earth data. So different kinds of raster and vector data are available over here, which can be used. This, please, you know, bookmark this site, the one that we used most frequently, because we can download all kinds of satellite images from here, all from NASA. So you also have some from India, but mostly it caters to all images from NASA. And the most popular one, which is the Landsat satellite. So the Landsat is the longest standing satellites in the world. So if you want to do any kind of, you know, time change analysis, we would always use a Landsat satellite image, right? So because I think you can go back as far back as 1980, you know, up until now. It's got 8 bands, which means it's a wide part of the electromagnetic spectrum that it covers. It has a 30-meter spatial resolution, which is, you know, good enough for all kinds of analysis, and it's free. The basic thing is free. So imagine Landsat 30 meters, you know, is free, but for LIST 30 meters, I had to pay several years ago, right? So there are these pros and cons, and this is one of the reasons why most researchers, they end up using a lot of the Landsat satellites for their data. So this is the biggest repository of satellite images, and you will find all kinds of satellite images from the different American satellites launched. You can all find them here. You need to have an account. And once you start off an account, you can, you know, there are various ways, either a bounding box, or, you know, you can put in the latitudes and longitudes and then, you know, download the image that you want. So of course you need a good internet, but that's about it. So any kind of satellite image is easily available. So I'm not audible. Dr. Nimbalkar, I'm not audible.
Well, now you are audible.
Okay.
No problem.
Okay. So I don't know why the problem is. Yeah, so please, you know, have an account here, because this is one of the biggest sources that you have of, the biggest sources that we have for, you know, satellite images, along with the Sentinel one. So the Sentinel is a bit higher. It's 10 meters, and I'll show that to you also later as well. And then we have OpenStreetMaps. Now, this is really fantastic, because while those sites, they actually give us the satellite images, we also need vector data. For example, you need roads, you need hospitals, you need schools, or, you know, you need police stations, or you need dams, you know, canals. So all kinds of data, and this can be easily got from OpenStreetMap. So all kinds of vector data is possible for you to easily download from OpenStreetMap. All of these have their own tutorials. So you can easily look through those tutorials, and of course, all of them need to have an account, and then you can download your data. This is also interesting. Though the last time I used it, I found that the data for India was pretty coarse. But if you are doing analyzing something at the level of the national level, it's good enough because the smaller errors don't matter then. So this is socio-economic data, and this is again also part of NASA. And here again, they have a lot of resources that you can use. This is all for free. So it's huge amount of data that NASA makes available for free for researchers. This is very interesting data because very often we need elevation. Yeah, we need, for example, you need a digital elevation model for something. So this open topography allows you to download elevation data. And we have freely available, we have two kinds of elevation data. One is SRTM and one is the Shuttle Radar Topographic Mission, and one is ASTA. So both of these can be downloaded, but also from their individual sites as well. Now, very often as researchers, we need other kinds of data. For example, I want solar insolation, or I want aerosol optical thickness. So other kinds of data, which is obviously not possible for me to measure. And these kind of atmospheric parameters, they can be got from the NASA Earth observations. So if you want to study air pollution, PM 2.5, you can use aerosol optical thickness and convert it to get PM 2.5. So all these kinds of data that, you can do fantastic analysis, you can download it from the NASA Earth observation, the NEO, as we call it, the NEO site. This is also part of the European Space Agency. And the earlier one that I showed you was the toolbox. The toolbox is basically like the software that you're using. And this one, which is the Copernicus Open Access Hub, it allows you to download images. And for free, you can see here, provides complete, free and open access to Sentinel-1, Sentinel-2. These are microwave images. And microwave images, they are basically you can even sort of the multispectral images, they need daylight, but this does not. So even if you have a phenomena which is occurring at the night, you are still able to, get that kind of data. Then you have Sentinel-3 and new one, Sentinel-5P as well. And all of this data can be downloaded. All of them have user guides, very, very friendly, very, very, detailed. But all that you need is the time and your mental bandwidth, to process all of this thing. This is Terra. This is, we call it this as Terra. Now here it's there are other different kinds of data associated with people. So associated with people and different kinds of environmental data. So it generally has population census, temperature, precipitation, climate data. There might be a little cost when you want to use it over a small area, but if you want to use it at a national level, it's fine. There's also land use data. So most of our students, spend times, and since we work on several projects, also for student theses, we have a good idea of, where the data is scarce and where it's fine, and, which one can be used and not. It's all been a process of trial and error over so many years. This is interesting because one of the data sets that I use from the FAO Geo network is soil data. So in India, the soil data is only available with the National Bureau of Soil Sciences. And till date, that data is not digitized. So if I want to have a soil map, a very fine soil map, for various purposes, I don't have anything. Either I go out and make those measurements and interpolate them, or I can go to the FAO network that has a slightly coarse soil map, but it's the only digital soil map that's available. And so this is very good for that kind of soil data. This is this is the Indian portal. So in the last few years, it has really developed, I would say, quite a lot. So Bhuvan does not only have a hydrology project. I just took a snapshot because it's related to the theme of your workshop, but Bhuvan has tons of other data. So mostly with this, visualization is very easy. And I have found that download is not always completely possible. So certain amount of data, of course, can be downloaded, but not as freely as we do it with the European Satellite Agency or with NASA. But yes, it still has got a lot of data, and this is the Indian version of Google Earth. So I'm sure you're all familiar with Google Earth. So Bhuvan is the Indian version of Google Earth. It's fantastic because it's got a lot of systems, and it also showcases what India actually is doing at a village level, with geospatial data. I think you have Dr. Patil coming and speaking to you on one of these days, and he would give you a very good idea of how they're actually using this at even the lowest level in India. So you can see the wide range of technologies that are being developed in the use of this data as well. Yeah, but you can explore this. For example, flood early warning, evapotranspiration, glacial lakes, snow melt, modeling, irrigation management, a lot of data related to this, and even operations related to this are possible from this particular site. Then you have the SRTM, and this is one of the widely used 3D elevation data that we have.
Hello, madam. Hello. Hello.
These are some of the, these are the two digital elevation models that you can directly download for any part of the earth. This is the site for downloading the nightlight data, as I told you. So let's say you want to study the effect of the electrification program in India. I mean, you don't need to do surveys. All that you need to do is to download these nightlight images, and you can easily find out which villages still don't have electricity and which still have, because it picks up the lights. And like I said, we also use it as a surrogate for GDP, but it can also be used by itself, for various kinds of applications, setting up businesses, to understand where electricity is and what opportunities are. So all kinds of data, all kinds of analysis can be made from this kind of data. This is MOSDAQ. Again, this is meteorological and oceanographic satellite data. So this is really unique because, as you can see here, you can get aerosol optical depth, normalized difference vegetation indexes, because this is again useful for vegetation analysis, and a lot of other kinds of data that you normally don't get from other satellites. So these are some kind of data that you can download here from here as well, from the ISRO initiative. You also have Giovanni. Now here again, this is an important data set for these kind of data. For example, data related to the cryosphere or to hydrology or to ocean biology. So it has got different kinds of variables. And sometimes we always need, most times we always need these variables, in our analysis. So aerosol data or atmospheric chemistry or dynamics, and all of this data, can be, easily downloaded as well. This is a site put up by WWF, Worldwide Fund for Nature, and they have this complete data set on hydrosheds. So you want hydrosheds, across the world. They have derived these hydrosheds from the SRTM. I showed you that. So if I have a SRTM DEM, I have to run a couple of steps before I can derive the watersheds. But here the watersheds are readily available. So anybody of you, would like to work on this, so it's something that you can directly download. So as you can see, the knowledge of this kind of data, what is available out there is really good, because you don't have to spend time and effort and money into actually recreating these data sets. It's all there and it's available. My most favorite site, because I've struggled with this, getting village boundaries. And I'll just narrate a little incident over here. So when I started working on this, I think about 5 years ago, everybody said, oh, village boundaries you can only get from the Survey of India. So we wrote to the Survey of India, and as you know, with the government organization, there are always a long process. We had to pay 1.5 lakhs because I wanted the village boundaries of a couple of districts here in the Western Ghats. And when I got that data 6 months later, it came with a letter which says that all of the Survey of India does not vouch for the authenticity or the boundaries of the data that they have given. And that really set me thinking. So we spent 1.5 lakhs. They didn't inform us, they didn't tell us this earlier. And they now say that, okay, this is what we have, but it's not verified on the ground. And then about, I think a year later or so, I hit upon this site, which is basically a crowdsourced site. So you have people working together to actually map village boundaries, and they are verified village boundaries. So I downloaded what I got from here. I checked it against a verified source that I had in another state, and it's fantastic. So this is what I show everybody, that yes, Indian village maps are available on this website, and they are verified and they are accurate. So even if you compare the maps to any government map, it's absolutely fine. So this is actually what the power of collaboration and crowdsourcing can really do. Census data, which is again very, very useful. But now, of course, we have the digital census data here. And I think you would find this very, very useful for downloading digitally all kinds of census data when you want to use it in your analysis. We have MiniSAS, another one that this is again a citizen science project that actually uses small biological organisms as indicators of water quality. And the United Nations now has actually approved the use of this technology for monitoring water bodies across the world as part of indicators for the Sustainable Development Goals. So this is again fantastic. So you can download water quality, from this MiniSAS website. So it's authenticated because it depends upon the biological animals which are found there, and there's a specific method to that as well. And the India Biodiversity Portal, I don't know how many of you would be into this, but we use it quite often because we have data about species here that we can easily use in all other kinds of analysis. There are tons of other websites, but these are the ones that I use most commonly. I find them very useful. I'm sure there are others as well, but that one can really use. So what I spoke to you about until this time is the way GIS was, what it is, and what the data sources are. But in the last 4 to 5 years or so, there have been new technology trends. And one of the new technology trends, I put this as 5. One is the real-time data revolution. So Uber, Ola, they all use data real-time, to know where you are. And this brings in a completely different data source. There's also been a miniaturization of technologies. We have drones, we have sensors, and sensors are bringing in a large amount of data in real time. We also have the proliferation of new mobile geospatial sensor platforms that again allow us to collect data in the real time and use it in our analysis. The advancement in the IT and the wireless network means that so there's a proliferation of these networks that allows us to actually plug the data that comes from the above 3 into our geospatial system. And obviously today, because of the cloud, we have an advances in computing capacity that allows us to process petabytes of data as well. And this really has changed the face of geospatial technologies. So what we're looking at today is what we call as geospatial big data. So data that comes in with a very large volume and speed and different kinds of data. I have data from Google search, I have data from Twitter, from Instagram, from Facebook, from sensors, from mobiles, from GPS locations, because you look at people today, they want to tell the whole world what they are doing and where they are. And then people like us would like to use this data for different kinds of analysis, right? So there's huge amount of data that's coming in that's changed what we can actually analyze. So we're all familiar with this, probably we do edit, maybe your kids do the edit, or maybe you do the edits, but we all want to say what we are. We all want to edit, 20 years ago, somebody would have thought of this as a very foolish thing to do, but everybody does this today. And this is what I call as an unintentional data generator. So you are correcting something, you're dropping a pin somewhere, and this is generating a certain kind of data. We also have the rise of the crowd, citizen science, everybody wants to contribute. Everybody is wearing the Fitbits. A lot of health data is with a particular company. So, okay, I didn't get the comment, but we can talk about that later. So, this is something which really comes in. And now when I look at GIS, so I have my traditional thing, raster, vector, attribute, but now I have this new data source. And new data source means I need new analytical techniques and I need new platforms, right? And this is where GIS is really going today. So just to give you an idea, in 60 seconds, right? 60 seconds, you have all of this data coming in. And you think of yourself, most of us, maybe not all, most of us get up in the morning and, the first thing, one of the first things that you will do is to switch on your cell phone and either read the newspaper, if not messages, or whatever else it is. And whatever we do in our lives, we are leaving these digital breadcrumbs, and these digital breadcrumbs, they can all be harnessed into analysis.
Madam, you are not audible now. Hello.
We found that we are able to predict dengue faster than the ground data, that comes in just by harnessing the Google search terms and, subjecting it to certain checks. So IoT and the internet boom, the connectedness that we see today because of the pandemic, all of this is going to result in huge amount of data which comes in. And if you look at it, there are differences and the differences are huge and so are the applications. So generally what we have now is unstructured data, right? Which means it needs different kinds of algorithms. It's large amount of data. It flows continuously. Yeah. And therefore we need machine learning tools generally to analyze this data. So traditionally, if we were using different kinds of algorithms, today we are using machine learning to actually analyze all these different kinds of data. And this is where the data sources for GIS or geospatial technologies, it differs widely. So if you look at the traditional big data analytical techniques, we basically used, statistics. So we used regression, clustering, simulation, and so on and so forth. But if you look at it now, we know that these traditional techniques, they cannot handle volume, velocity, and variety. So if you have data, for example, from satellite image, you have data from mobile networks, I have data from the IoT sensors. A traditional algorithm is not able to handle these multiple different types of data sources. But if we have to make better decisions today, we have this data. So we need the algorithms and the platforms to be able to merge these different data sources together. So this is where all the non-traditional big data analytical techniques, they come on. There are many of them. I can't say that I have researched all of them, but we've used a couple, and I'll show you an example, of where we've tried to use this kind of thing. I read a very interesting case study, which is about this Google VR. So they said that if kids could wear the virtual reality glasses and cycle to school, the system can actually analyze what the children see and how accidents occur. So this can be used to build better roads and avoid accidents as well. So this is just one of the applications that are actually in work. They are in place today. So these different kinds of data, they will give rise to a whole new world of utilities. And then comes in Google Earth Engine. This is really fascinating, because we spent money on software like AirDAS Imagine, NV, S3, we have all of that in our lab, right? And then in comes Google Earth Engine, because I don't need a software. I don't even need computing power. I'm just plugging into their platform, and I can download images from anywhere across the world, nightlight data, Landsat data, LIS data, Sentinel data, everything, and I can analyze it using their platform. Okay, I just need to know Python to write the codes, but I can easily analyze it. So imagine, so I showed you all of those data sources, and 75% of them are all on Google Earth Engine. So this has really changed the way in which we actually analyze data. And it's very fast. I'll show you a project that one of my students did. Yeah, so this was the project that he did. We wanted to map wetlands of Maharashtra because 20 years ago, we did a project where we assessed the wetlands. And looking through literature, we found that wetlands of Maharashtra have not been assessed for the last 10 years. So we thought it's a good idea to use Google Earth Engine and see whether we can actually assess the wetlands. Simply because we have increasing number of urban floods. And one of the reasons is that wetlands are destroyed, making the land lose its ability to hold water and cause the floods as well. So normally, if we had to do this study, which I remember from 20 years ago, we had to have a team in all the districts of Maharashtra, phone them, ask them, "Mere bhai, data bhejo, ye kahan hai, wo kahan hai," get all that thing. It took us a year to compile. And this guy, using Google Earth Engine, he actually did a little analysis because the government of Maharashtra wanted to have this wetland data to actually declare Ramsar sites. And they needed to know, what wetlands are there and what is the status and so on and so forth. So over a period of 3 months, he wrote a code. And in 3 months, we were able to get, this kind of data of wetlands. So if you can look at our accuracy assessment, so we were sort of 3379, 3623. Of course, this is a student project. It can be, fine-tuned much further to get this kind of accuracy. Post-monsoon also, we were sort of pretty close. So it's easy to do this. So it's Google Earth Engine. We can analyze the whole state and get the data just in about 3 months that a decision maker can use. So it's changed the way, these platforms have changed the way we look at data and we analyze it. This is a very interesting slide, and normally I can speak on this for a whole hour, but just to cut short this to get you to understand this. So you look at the geospatial tech trends today. So you have these trends in computer engineering because there's a lot of advancements that's happening here that actually plugs in onto this side as well. You have sensing and observations, from new sensors in space, LiDAR, drones, web of things, crowdsourcing, all new techniques, all new sensing techniques, which again plug in here. You have societal geosciences. For example, you have autonomous vehicles, dynamic resource management, human activity modeling, pandemic modeling or tracing, and physical, which is precision geoweather, disaster risk reduction, climate change impact. So all of this, which you can combine with these technologies around here, and this creates absolutely new geospatial trends. So I can take 2 from here and I can take 2 from here and I have a new application. Yeah. So whether it's 3D model twin cities, we have digital twins as we call them today. So you can actually recreate an entire city the way you want it as a digital twin and plan your utilities. So which uses technology from here and technology from here as well. So all these different kinds of things. So with the human interfaces, for example, VR, MR, AR, all this kind of thing, natural language processing, which is very useful, spatial thinking, AI. So all of these things over here. So these are completely new, and just taking 1 or 2 from here, combining them with, the methods gives us something else. So I think there's a lot more work that's happening in this arena in the field of, GIS now. Yeah, and this is the project that we did. So we use this term community remote sensing. It's not my term. The term exists. The scientist called as Bolos, who actually first brought out this term. And what he brought out was, can we integrate different data sources along with human crowdsourcing to design better algorithms? So we actually applied this to the city of Pune, where we wanted to see what kind of algorithms could be designed to have a better surveillance system for dengue. So normally in this process, what we found out would be quite shocking. The data from the field, it comes through the ASHA workers, if you know them. And they report to the district medical officer. So most often they just phone and they say ki saab aaj 2 cases hai, saab aaj 3 cases hai, and of course laboratory confirmed whatever, and it comes to them. We went to the DMO and we said, we'd like to have a look at the data that the ASHA workers are actually sending you. And he dilly-dallied and, said, nahi, aaj aao, kal aao, till, we finally got to pin him down. And then we understood that he does not have a system for actually putting this data together. So it's all over the place. He says, madam, ye kamra hai, ye files hai, agar aap le sakte ho, usme se aap le lo. I don't know how they report, don't ask me about that. So we actually took a group of students, sat there, pulled out all the data because we needed it for verification, made our own tables. And at that point in time, we realized that having an app for the ASHA worker would be very useful. So I got one of my students to design what we called as the ASHA app, where we made a survey and found that almost 60% of them had got smartphones. So they could install this app, and the data that is input can directly go there into a system as well. Of course, they were quite thankful to us for that. So that's when I say sentinel data, it's the survey data from the ground. And of course, there were remote sensing data because the breeding of the malaria is related to the rise in temperature.
Hello, madam. Hello. Hello. Madam, not audible again.
Sorry?
For some time you were not audible again.
Okay. I hope I'm audible now.
Okay.
Yeah. So how do I make it, very easily available to a doctor? So it obviously means it has to have a interface. So remote sensing data combined with data from the ground, combined with Twitter data, because we found that at least in urban areas, people tweet, I have dengue. Tomorrow, if the doctor says you have dengue, the first thing that you will do is to go on to Google and search. Of course, I'm not a big tweeter, so I don't do that, but I will definitely search. And therefore, we integrated the Google search term data, to the Google Trends data as well. So as you can see, we sort of combined all of this through an automation process. We also worked with a US, the Dakota University, for certain parameters over here, and put this together, as well as added a public reporting platform. So if, for example, I have dengue, I can go there and, report it. It's in an experimental stage, but it showed us that, these different kinds of data can be put together. And what is interesting is we found that we could predict the peak for dengue 1 week before the municipal corporation could do. And 1 week is a long enough time for them to be able to, take corrective measures, in a particular locality. So the limitation, of course, is we were using MODIS data, and MODIS has a drawback, in the monsoons. So we're still trying to, work around, what we can do for that. But at least we have a prototype, that sort of works. Yeah. And this is, I think, the newer way, the new trend in which geospatial technologies will go. So just coming to the last part before, we can have questions. When I first started working with the Department of Science and Technology, I was quite well aware of the challenges that are there in the educational sector. And one of the suggestions that I made was that the capacity building program that the DST had could actually try to focus on using open source, simply because when teachers come to a training program, and they are taught a commercial software, they may not necessarily have access to the same commercial software in their own workplaces. But if the training is done using open source software, the teacher has an ability to teach and also use this software, with their students. And actually, this led to the development of this portal. It's the DST, you can just type in dst.iget.in. And as you can see here, we have a large number of tutorials and resources. And I'd just like to, stop here and reshare my screen. reshare another screen. Yeah, can you see this one? Can you see this one?
Yes, madam.
Yeah, so if you can look at this here, there are tutorials. So that's understanding GIS. We have about 10 odd, and it's continuously a work in progress. It's being updated. So remote sensing, you know, we have a lot of people have contributed. We have still several more which we are uploading. But the beauty is that, you know, for example, if I go into any of these tutorials, I hope you can see the screen when I share it. You know, you can download the PDF and you can download the data, right? And if I open the PDF, I think the window changes, but yeah, it's downloading here. So when I open the PDF, it's a step-by-step instruction to how I can actually do this particular tutorial. So we have the data already here given to you. You can work with the PDF and, you know, you can learn this, you know, on your own. And this particular portal now is the DST runs summer schools in geospatial technologies. So we have had 2 rounds in the past. So I'm just going to click on the previous round that we had here, where the institutions who are part of the program are selected through a very rigorous process by the DST. And each of these institutions, they conduct 3-week summer school programs completely with open source software. And the programs are at 2 levels, level 1, which is basic, and level 2, which is advanced. So we have specialized summer schools. For example, Dr. Thakural, who you met today, is part of the program, and he runs, this year he will be running a Geo Innovation program. Or you met Dr. Ramesh yesterday, he's from Suratkal. He's also part of the program, and he will be running a level 1 program. So I think it's taking some time to come up, but you could check this on your own. And as you can see here, for 2021 and 23, within this month, we are uploading the new training cycle. And there are a lot of programs here that you could be a part of in case you feel that, you know, you're really interested in learning this particular technology. There is no charge for any of these programs. Some of the institutions are running the programs online because of the pandemic. Yeah, there it is. So for every institution, you have the registration form and feedback form, but there's a common application form. So if you want to apply to a particular institution, for example, IIT Chennai, in the form, you need to tick mark and say, I want to attend the program at IIT Chennai. And then there's a selection process. Every center takes in about 25 participants. You know, you can attend the program. So the program at IIT Chennai was really good because it was on marine geosciences. And I think this is one of the only places in the country that has that kind of expertise. They will be running the program again this year as well. That's a level 2 program. And for a level 2 program, a certain familiarity with GIS is needed. But if you don't have that familiarity, you can always attend a level 1 program as well. And this year, the DST has also announced a new program, which is called as the Geo Innovation Program. And that's what Dr. Thakural also will be running. So the Geo Innovation Program is to bring in innovation into this field. So the DST wants to look at new ideas, and we've been able to rope in industry into this, FICCI and AGI, Association of Geospatial Industries. The idea is that if it's a participant 35 or less than 35 with a PhD degree has an innovative idea, he can present the idea before a committee and he will be funded, you know, to even take it to the final step of production as well. And that's why industry is in here. So it's a Geo Innovation Challenge and it will be run all across the country. There are 9 Geo Innovation Challenges, theme specific. So please watch this site in the next 15 days or so. A lot of training programs will be applying here. So if you feel interested through this FDP and you feel the need to learn more, you can always, visit any of these sites and understand. So as a last part, what I wanted to show you was just the interfaces with the softwares. So I'm just going to share the screen again. So it doesn't really work very well. This is the ArcGIS interface actually. So so here, so this is our DEM, and from a single DEM, using a boundary, you are also, of course, or without a boundary, you are able to extract the watershed. And of course, you can do a lot more analysis on this. So as you can see here, this is what we call as a vector data. So this is a polygon. You can see here, this is a point. And you can see here that this is basically a raster data. And the heart of ArcGIS is basically in its toolbox. So I'm not going to open this because it takes some time, and more so when I'm online. So this is a toolbox, and this particular, let's see what happens and how long it takes. And this toolbox basically has got a huge set of tools, that I can use for performing, various kinds of analysis. So you can see here that I have a 3D analyst, which has raster, vector analysis, city engine, simple analysis tool. So this is where spatial analysis comes in. I have cartographic tools over here, and so many more. Here, spatial analysis is a whole big set. I mean, I must admit that I have also not explored all of these because I think it takes more than a lifetime. But I know most of these, but I wouldn't say that I have explored all of these. It's just too huge to do it. There are a lot of data management tools, and within each, again, you have several tools as well. So it's an enormous amount of tools which are there. But what's also interesting is can you see my QGIS screen now, or you can't?
QGIS.
No? Okay,
No, madam.
I'll just share it again. So this is the QGIS screen, yeah? So if you look at it, it's not really, very different or very difficult, yeah? So once you are familiar with any software, mostly everything is there. The concept needs to be, just clear. Now, just like the toolbox in ArcGIS, this one works with plugins. Now, it has got enormous number of plugins, and there is also one, I think there is QSWOT. So you can also, you plug in raster data with this. So here you can just, like the toolbox, use various kinds of plugins to, there are tons, and I mean, they're here and they're much more that you can keep downloading as you want. So whether you use a commercial software today or a free open source software, I would say that free open source software has come a long way since when it was really unwieldy. And today, of course, an ArcGIS is always very smooth, no question about that. But this is free. So that's the big difference. And it also does the same amount of work. Yeah. So it's pretty easy to use this once you're familiar with it. And we have a site, and there are many other sites like that. So once you start working, all the different sites, and it becomes really easy for you to use it. Okay, so with that, I come to the end, I think, of my, let me just check. Yeah. So yes, with that, I come to the end of my presentation, and I'm happy to interact and answer any questions if there are.
Yes, any questions, participants? Any questions? If you can put it in chat box. I think, madam, most of them, they want your this
Yes.
PowerPoint presentation.
Yes, yes. I'll share it to you and you can share it with the group.
Okay, okay, madam.
No problem
So,
at all.
okay. So, on behalf of all the participants and our institute, our department, I'm very much thankful to you, madam. A very nice, wonderful presentation and lot of information about this GIS and the various this open source softwares and data sources. It is very wonderful presentation, madam. Thank you. Thank you very much.
Thank you. Thank you very much. Thank you.
One question, madam. Ek minute. Somebody is asking.
Yeah, I'm free for. I'm happy to have questions. That's why I ended
How
it
can
15
we
minutes
predict
early.
urbanization? There is a
Okay.
question.
Okay, so that's pretty easy to do that because one of my PhD students worked on it. If you Google my name and Pune in urbanization, the paper will show up. So basically, the kind of method that we used was, you have these cellular automata based algorithms. So by having a land use land cover map of particular periods in time, you apply different algorithms and regression techniques to it to be able to predict the future. And in this process of predicting the future, we also identify drivers of change. So the first step would be to have a land use land cover map. The second step would be to pick out the drivers. For example, drivers could be the SEZs, the socioeconomic zones. Drivers could be roads, drivers could be schools, drivers could be industries, drivers could be government policies. So what we generally do is to use regression techniques to understand how these drivers have affected the urbanization as we know it in the past. And then we design the algorithm to predict for the future. So in doing this, we actually use cellular automata techniques. So it's a little high level of analysis, but not something that you cannot do once you really understand it. So like I said, we have 3 papers actually on this specific topic that deals with predicting the urbanization of Pune. The first one deals with gives the status quo of land use land cover. The second one, speaks about what drove the change, and the third one is, a prediction of how things can work. So you could look that up. But it's a combination of remote sensing, GIS, spatial analysis, and programming.
Okay, madam.
Yeah, I mean, please feel free. Please make use of the DST training programs which are there because they are very fantastic. The organizations who are conducting these programs are really top class, and the syllabus is standardized across the country. So whichever institution you choose, it doesn't matter. You can choose the one which is closest to your place and make use of it. And some of them this time are running it in the online mode. So if you want to attend online, that's what you can attend as well. I'm checking, is it necessary? Yes, yes. It's mandatory to perform ground truth check every time, right? Because of the nature of the remote sensing data, there are always anomalies in it because the resolution determines accuracy, and therefore there are always anomalies. So without ground truth, we will not put any data out in the platform. But today we can actually use Google Earth, itself to perform the accuracy assessment, because Google Earth allows us to go back to about year 2000, and therefore this also can be used as an accuracy assessment. But otherwise, yes, accuracy assessment is absolutely essential when you are putting out a geospatial result. Yeah, so my contact details, I can just put it in the chat here. I'm just putting my email ID in the chat. So yeah, you have that.
I will share them.
Yeah, fine. Yeah.
Okay.
Okay. Can you track the location of smartphone users? Yes, but you would need the TRAI permissions for that. I mean, all of that data is not really available in the open domain. Image classification using Google Earth Engine. So Google Earth Engine basically uses, Python, and there are several training programs on that. So once you know the language, then you are very easily available to analyze images. But to begin with, if you want like simple functions, not complete land use land curve analysis, but let's say you want to do NDVI or some simple function like that, the code, as with other codes, is available on the internet. But in the long run, it's always better for you to be able to write your own codes with Python.
I think
Yeah.
now there are no questions, madam.
Yeah. Okay.
Okay. Thank you very much, madam. Once
Thank you
again,
very much. Thank you very much.
it is
Yes.
very wonderful presentation. Okay.
Thank you.
Okay.
Thank you.
Thank you.
Bye-bye.
Thank you, madam.
Bye.